Approximately 260 million years ago, the planet Earth supported a living world of extraordinary complexity. The continents, still fused into the supercontinent Pangaea, stretched from pole to pole across a single landmass roughly 200 million square kilometers in area. The oceans that surrounded it, collectively referred to as Panthalassa, covered the remaining surface of the globe, reaching depths comparable to modern ocean basins and sustaining marine ecosystems that had been building in diversity for hundreds of millions of years. This was the Middle Permian period, and by every measurable biological standard, life had reached one of its most elaborate expressions since first emerging in the Cambrian seas some 300 million years earlier. The Permian was not simply an age of abundance, it was the product of deep time of evolutionary trial and refinement operating across timescales difficult to fully conceptualize. Species had survived multiple prior extinction events, recovered, diversified again, and in doing so had produced ecological architectures of considerable stability. Food webs were layered. Ecosystems were interconnected. The organisms that moved through Permian landscapes and seas were not primitive experiments, they were highly adapted, deeply integrated components of functioning biological systems. Before we continue, take a moment to consider where you're watching from which country and how distant it is from a time when nearly all life was pushed to the edge of disappearance. If this kind of journey holds your attention, consider subscribing to follow the rest. It's always revealing to sense how far these stories travel, soften the lights, settle into stillness, and let the present recede as the air grows heavy and the oceans fall silent, carrying the slow, fading echo of a world losing almost everything. On land, the dominant vertebrates were the synapsids, a broad and successful lineage that represented the evolutionary stem from which mammals would eventually arise. By the Middle Permian, synapsids had diversified into dozens of distinct families, occupying a wide range of ecological roles. Among the most recognizable were the therapsids, a group that had largely replaced the earlier, more reptile-like pelycosaurs. Therapsids ranged considerably in form and function. Some were large, heavily built herbivores capable of processing tough, fibrous vegetation. Others were active predators with differentiated dentition teeth specialized for gripping, puncturing, and processing prey in ways that earlier vertebrates had not achieved. The dicynodonts were among the most ecologically significant herbivores of this period. These animals, characterized by a pair of prominent canine tusks and a keratinous beak, were highly successful grazers and browsers. Evidence from fossil sites across what is now Russia, South Africa, and parts of South America indicates that dicynodonts were abundant and geographically widespread. Some species reached body masses comparable to modern large mammals. Their digestive systems, inferred from body proportions and skeletal structure, appear to have been adapted to process large volumes of plant matter, a necessary capability in ecosystems where terrestrial vegetation formed the base of the food chain. Alongside the dicynodonts moved the Gorgonopsians, predatory therapsids that occupied apex positions in many Permian terrestrial food webs. Gorgonopsians were powerfully built, with large skulls, deep temporal fossae indicating strong jaw musculature, and prominent saber-like canine teeth. The largest known genera reached body lengths of approximately 3 meters, placing them among the dominant land predators of their time. Their limb structure, while retaining certain ancestral features, shows evidence of an increasingly upright posture compared to earlier synapsid lineages, a modification that likely improved locomotor efficiency and sustained activity levels. The Dinocephalians, an earlier therapsid group, had largely declined by the late Middle Permian, but their prior dominance had helped shape the ecosystems into which later groups expanded. Their disappearance, part of a smaller, earlier extinction pulse approximately 260 million years ago, had already demonstrated that even dominant, well-established vertebrate lineages were not immune to large-scale environmental disruption. The ecosystems that filled in after that event were, in many respects, more derived and more ecologically specialized than what had come before. On the forest floors and in the understory of Permian vegetation zones, smaller animals moved through environments shaped by a flora quite different from anything alive today. The dominant plants of the Permian included seed ferns, not true ferns, but seed-bearing plants with fern-like fronds, as well as chordata-lians, gymnosperms that formed tall, straight-trunked trees in certain regions, and glossopterids, a group particularly prevalent across the southern portion of Pangaea. These plant communities supported not only large herbivores, but entire networks of smaller organisms, insects, arachnids, early reptiles, and amphibians that occupied the lower tiers of terrestrial ecosystems. Insects had diversified enormously by the Permian, having already passed through an earlier peak of gigantism in the Carboniferous. By the Permian period, insect body sizes had generally decreased in correlation with declining atmospheric oxygen levels, oxygen content, estimated at roughly 23% in the early Permian, and declining gradually towards 16% by the period's end, directly constrained the respiratory efficiency of tracheal systems and therefore set upper limits on body size for air-breathing invertebrates. Despite this constraint, insects remained diverse and ecologically important, occupying roles as decomposers, herbivores, and prey for larger animals. Amphibians, though no longer the dominant land vertebrates they had been in the Carboniferous, retained significant ecological presence in certain Permian environments. The temnospondyls, a large and varied group of amphibious tetrapods, persisted across the Permian in freshwater habitats and near coastal regions. Some temnospondyle genera reached considerable size, with skull lengths exceeding half a meter in certain lineages. These animals occupied predatory niches in aquatic and semi-aquatic settings, feeding on fish, smaller tetrapods, and invertebrates. Their dependence on moist environments made their distribution patchy across the increasingly arid interior of Pangaea, but in riverine, lacustrine, and coastal zones they remained abundant. The early reptiles of the Permian, distinct from the synapsid lineage, were generally smaller and less ecologically dominant on land during this period, though they were present and diversifying. Anapsid reptiles, including the ancestors of later groups, occupied various niches across Permian environments. Their populations, while less conspicuous in the fossil record than the large synapsids, contributed to the overall biodiversity that characterized healthy Permian terrestrial ecosystems. Beneath the surface of Panthalassa and in the shallower seas of the Tethys, the ocean that partially separated the eastern margin of Pangaea, marine ecosystems had achieved comparable levels of complexity. Reef systems, built not by modern corals but by rugose and tabulate corals, alongside bryozoans and brachiopods, supported diverse assemblages of filter feeders, mobile invertebrates, and predatory fish. Brachiopods' lampshells were among the most numerically abundant marine invertebrates of the Permian, with thousands of described species colonizing seafloors at varying depths. Their ecological success across hundreds of millions of years indicated a fundamental compatibility with the range of ocean conditions that had prevailed through much of the Paleozoic. Crinoids, stalked echinoderms that filtered organic particles from the water column, grew in dense aggregations on Permian seafloors. Bryozoans' colonial filter feeders formed encrusting and branching structures that provided habitat complexity for smaller organisms. Ammonoids, already an ancient group by the Permian, navigated open water and shallow shelves, serving as both predators of smaller invertebrates and prey for larger marine animals. Sharks and bony fish occupied higher trophic levels, with some lineages reaching body sizes of several meters. The overall picture that emerges from the Permian fossil record is not one of a world on the verge of collapse. The ecosystems of this period were stable, diverse, and deeply interconnected. Species had co-evolved across millions of years. Competitive relationships, predator-prey dynamics, and nutrient cycles had been refined through long intervals of relative environmental stability. The biological systems of the late Permian represented the accumulated product of nearly 300 million years of evolutionary history on land and far longer in the sea. Yet stability in geological terms is always conditional. It persists only as long as the physical and chemical parameters within which life evolved remain within tolerable ranges. Temperature, atmospheric composition, ocean chemistry, and sea level are not fixed constants. They are dynamic variables, subject to perturbation by forces operating on timescales far exceeding those of individual organisms or even entire species lineages. The Permian world, for all its biological richness, existed within a set of physical boundary conditions. Those conditions, by the close of the period, would undergo changes of sufficient magnitude and speed to exceed the adaptive capacity of nearly every living system on Earth. The diversity that had accumulated across hundreds of millions of years, the layered food webs, the reef communities, the complex terrestrial vertebrate faunas had no evolutionary preparation for what was approaching. The organisms of the late Permian could not anticipate disruption. They continued, as living systems do, in the patterns shaped by the world they had always known. The geological record preserves that continuity with considerable clarity. Dense fossil beds from the middle and early late Permian containing abundant, diverse, well-preserved organisms representing ecosystems functioning at or near maximum ecological complexity. That record does not diminish gradually. In stratigraphic terms, it ends with a sharpness that geologists continue to study in detail at sites across every continent. What had taken hundreds of millions of years to build would, within a time frame measured in thousands to tens of thousands of years, be reduced to a fraction of its former self. The mechanisms behind that reduction were planetary in scale, rooted in the deep interior of the Earth itself, and would operate through cascading physical and chemical pathways affecting every environment on the surface of the globe simultaneously. Pangaea was not a uniform landscape. Despite being a single continuous landmass, it encompassed an enormous range of environmental conditions that varied systematically with latitude, distance from the ocean, and elevation. These gradients shaped the distribution of life with considerable precision, producing distinct faunal assemblages adapted to markedly different physical circumstances. The organisms of the Permian did not inhabit a single world so much as a mosaic of worlds, each defined by its own temperature range, moisture availability, and seasonal extremes. The interior of Pangaea presented some of the most physiologically demanding terrestrial conditions on Earth during this period. At distances exceeding 1,000 kilometers from any coastline, distances easily reached within the vast central regions of the supercontinent, the moderating influence of the ocean was effectively absent. Without that buffer, seasonal temperature swings became extreme. Evidence from sedimentary deposits and paleosol records indicates that interior Pangaea experienced summer temperatures potentially reaching 45 to 50 degrees Celsius at mid-latitudes, while winters in the same regions could drop well below freezing. Annual temperature ranges of 40 degrees or more within a single location were likely common across broad interior zones. Rainfall in these interior regions was sparse and irregular. The same continental geometry that produced thermal extremes also disrupted atmospheric moisture circulation. Prevailing winds, by the time they reached the deep interior, had already deposited most of their moisture content over coastal zones. What remained was insufficient to support dense, continuous vegetation. The result was a landscape of semi-arid to arid conditions across much of central Pangaea redbed sedimentary sequences from this period, tinted by oxidized iron minerals, preserve clear evidence of seasonally dry, oxidizing environments where water was a limiting resource for nearly all biological processes. The animals that lived in these interior environments were, by necessity, physiologically and behaviorally specialized. Among the most successful interior adapted forms were certain Dicynodont genera capable of surviving extended dry seasons, possibly through behavioral dormancy or physiological water conservation strategies inferred from their compact, robust body forms. Some evidence suggests that certain Permian herbivores may have migrated seasonally, moving toward higher latitudes or river valleys during dry periods and returning as moisture availability shifted. Whether such movements were obligate or opportunistic remains an area of ongoing research. But the geographic distribution of fossil material indicates that some large herbivores ranged across considerable distances during their lifetimes. Predators of the interior faced compounding challenges. In environments where prey populations fluctuated with seasonal resource availability, a carnivore's survival depended on either following prey movements or tolerating extended periods of reduced food intake. The Gorgonopsians, whose fossil remains are found across a wide range of Permian paleo environments, appear to have been capable of surviving in relatively arid conditions. Their body proportions deep-chested, with relatively long limbs, for their lineage suggest a capacity for sustained locomotion that would have supported pursuit hunting or wide-ranging foraging behavior across open resource-sparse terrain. The Cynodont therapsids, a group that would eventually give rise to the mammalian lineage, were present in Permian interior environments as smaller-bodied predators and possibly omnivores. Their fossil record from this period is less extensive than that of the larger therapsid groups, but the morphological features they possessed, including evidence for differentiated teeth capable of processing varied food types and skeletal indicators suggesting relatively high metabolic activity, position them as adaptable generalists. This ecological flexibility, modest in the context of the Permian world, would later prove significant under conditions that eliminated specialists. Coastal and equatorial regions of Pangaea supported fundamentally different biological communities. Where the supercontinent met the waters of Panthalassa and the Tethys, moisture was abundant, temperatures were moderated by oceanic influence, and vegetation was correspondingly dense. Forests of chordate and seed ferns grew in zones where annual rainfall was sufficient to sustain continuous canopy cover. These environments supported higher species diversity per unit area than the arid interior, and the fossil record from these regions reflects greater taxonomic richness in both plant and animal assemblages. Temnospondyle amphibians were concentrated along these coastal and riverine corridors, their physiology anchoring them to environments with reliable water access. Large temnospondyls occupied ambush predator roles in river systems and delta environments, lying in wait for terrestrial animals that approach the water's edge. Their body plans dorso-ventrally flattened, with eyes positioned near the top of broad skulls, were functionally similar to those of modern crocodilians, reflecting convergent adaptation to semi-aquatic predation. Some genera reached total body lengths of 2 to 3 meters, making them formidable components of their local food webs. The equatorial belt of Pangaea, running roughly along the paleoequator, was characterized by conditions considerably more humid than the mid-latitude interior. Paleoclimate reconstructions based on plant fossil assemblages and sedimentary faces suggest that equatorial regions experienced rainfall patterns more consistent with tropical or subtropical climates, though the absence of modern-style tropical circulation patterns means direct comparison with present-day tropical systems is imprecise. Vegetation in these zones was seasonally variable, but consistently more productive than interior environments, supporting higher densities of large herbivores and the predator populations dependent on them. Along the southern margins of Pangaea, the region corresponding broadly to what would become Antarctica, Southern Africa, South America, and Australia, a distinct biogeographic province had developed, characterized by the dominance of glossopterid flora. Glossopteris and related genera formed forests across high southern latitudes, their deciduous habit likely an adaptation to polar light cycles involving extended periods of darkness in winter. The animal communities associated with glossopterid forests were correspondingly distinctive, with certain dicynodont and theracephalian therapsid genera showing distributions closely correlated with this southern vegetation zone. This geographic differentiation in Permian life had important implications for the resilience of the overall biosphere. Distinct regional faunas meant that no single environmental event could simultaneously affect all populations of a given species in the same way. Animals adapted to interior aridity were already tolerant of temperature extremes. Animals in coastal regions were buffered by oceanic thermal inertia. Southern high-latitude fauna had adaptations to seasonal light and temperature variation. This spatial heterogeneity in adaptive strategies represented a form of biological insurance distributed across the surface of the planet in ways that had historically allowed recovery from regional disruptions. What this architecture was not designed to withstand, what no amount of geographic distribution could protect against, was a disruption operating at planetary scale, affecting atmospheric composition, ocean chemistry, and surface temperature simultaneously and persistently across all latitudes and all environments. Regional specialization provides resilience against regional stressors. It provides no protection when the stressor is global and the change is faster than evolutionary response times allow. The creatures of Pangaea had, over millions of years, filled every available ecological space with forms precisely tuned to local conditions. That precision was itself a vulnerability. Animals closely matched to specific temperature ranges, specific moisture regimes, specific vegetation types, and specific prey assemblages had little tolerance for rapid change in any of those parameters. The margin between optimal conditions and physiological limits was, for many species, narrow, maintained in equilibrium by the relative stability of Permian environments across the timescales relevant to individual populations. That equilibrium would not hold. The same deep interior of Pangaea that had shaped so many of its inhabitants' adaptations lay above geological structures that were, by the late Permian, approaching a state of catastrophic instability. The mantle beneath what is now northern Siberia was accumulating conditions that would produce one of the largest volcanic episodes in the planet's history. When that episode began, its effects would not respect the boundaries between coastal and interior, between north and south, between marine and terrestrial. It would reach everywhere. And the diversity that had taken so long to assemble the specialists of the arid interior, the predators of the coastal forests, The filter feeders of the shallow seas would have no mechanism to escape what was coming from below the surface of the Earth itself. The Permian world, for all its biological richness, operated under atmospheric conditions that placed measurable physiological stress on nearly every complex organism alive at the time. Oxygen, the molecule that powers aerobic metabolism in animals ranging from marine invertebrates to large terrestrial vertebrates, was not present in the atmosphere at the concentrations that characterize the modern world. Current estimates, derived from geochemical modeling of carbon and sulfur isotope ratios in Permian sedimentary sequences, place atmospheric oxygen levels at approximately 16% by the late Permian compared to the 21% that defines the present-day atmosphere. That difference of 5 percentage points may appear modest in absolute terms, but its biological consequences were substantial and pervasive across nearly every ecosystem on the planet. Oxygen availability governs the upper limits of aerobic metabolism. For terrestrial animals, the efficiency of gas exchange across respiratory surfaces, lungs, in the case of vertebrates, depends directly on the partial pressure of oxygen in the surrounding air. At 16% atmospheric oxygen, the partial pressure of oxygen at sea level was roughly equivalent to what a modern animal would experience at an altitude of approximately 2,700 meters above sea level. This is not an immediately lethal condition, but it imposes a persistent ceiling on sustained physical performance. Maximum aerobic capacity is reduced. Recovery from exertion takes longer. The physiological cost of activities such as pursuit predation, long-distance migration, and active foraging is proportionally higher than it would be under oxygen-rich conditions. For large-bodied animals with high mass-specific metabolic demands, this constraint was particularly significant. The Gorgonopsians, which occupied apex predator roles in many Permian terrestrial ecosystems, required sustained bursts of muscular effort to pursue and subdue prey. At reduced atmospheric oxygen, the anaerobic threshold, the point at which muscles shift from aerobic to anaerobic energy production, was reached more quickly, and recovery between high-intensity efforts was extended. This did not render these animals ineffective predators, but it placed boundaries on the intensity and duration of their activity that would not have applied under higher oxygen conditions. Smaller animals experienced the low oxygen atmosphere differently, but not necessarily with less impact. Insects, which rely on passive diffusion and muscular pumping through tracheal tube systems to distribute oxygen to tissues, are particularly sensitive to atmospheric oxygen concentration. The body size limits imposed by tracheal respiration scale directly with oxygen availability. Higher oxygen permits larger body sizes, as demonstrated by the gigantic insects of the Carboniferous period, when atmospheric oxygen reached an estimated 35%. By the late Permian, declining oxygen had already reduced maximum insect body size considerably from Carboniferous peaks. Many insect lineages were constrained to smaller body forms, which in turn affected their ecological roles, their reproductive rates, and their vulnerability to environmental change. In aquatic environments, oxygen stress expressed itself through a different but related mechanism. The solubility of oxygen in water decreases as water temperature increases, a physical relationship with direct consequences for marine and freshwater ecosystems. Permian ocean temperatures were already elevated relative to modern baselines, particularly in shallow tropical seas, where water temperatures may have reached 28 to 32 degrees Celsius in certain regions. At these temperatures, dissolved oxygen concentrations in surface waters were measurably lower than those found in cooler seas, compressing the habitable oxygen envelope for marine animals with high metabolic demands. Deep ocean waters, where circulation was sluggish and organic matter decomposition consumed available oxygen, showed evidence of periodic anoxia conditions in which dissolved oxygen fell to near zero levels across significant seafloor areas. The fossil record from late Permian marine sediments preserves indicators of these oxygen-stressed conditions in the form of laminated, organic-rich mudstones, a sedimentary facies that accumulates when bottom water oxygen levels are insufficient to support the burrowing organisms that would otherwise disturb and mix sediment layers. These laminated sequences, found at multiple locations across the Tethys and Panthalassa margins, indicate that anoxic or severely hypoxic conditions were not rare events in Permian oceans. They were recurring features of a marine system already operating near the lower boundary of the oxygen range tolerable for diverse bottom-dwelling communities. The vegetation of the late Permian was itself responding to environmental stress. Paleobotanical evidence from multiple continental sections indicates a pattern of floristic change during the late Permian that precedes the main extinction horizon, a gradual shift away from diverse, structurally complex plant communities towards simpler, lower diversity assemblages. In some regions, this transition involved the replacement of mixed forest communities with more open, seasonally dry vegetation types. In others, it manifested as a reduction in the abundance and diversity of seed-bearing plants with corresponding changes in the soil communities and herbivore populations dependent on them. This floristic deterioration had cascading effects through terrestrial food webs. Herbivores dependent on specific plant groups faced declining food quality and availability before the main extinction pulse. The dicynodonts, whose success had been built in part on their ability to process large quantities of tough plant material, were increasingly challenged by a plant community that was becoming less productive and less diverse. Evidence from body condition proxies in late Permian dicynodont fossils, including bone pathologies consistent with nutritional stress, suggests that some populations were already experiencing resource limitation prior to the context piece. Catastrophic events of the end Permian. Soil systems, which mediate the cycling of nutrients between the biological and geological domains, were also showing signs of stress in the late Permian. Paleosol sequences, ancient soils preserved in the rock record from this period, show evidence of increased erosion rates, reduced organic matter content, and changes in the microbial communities responsible for decomposition and nutrient mineralization. Healthy terrestrial ecosystems depend on stable, biologically active soils to process dead organic matter and return nutrients to growing plants. Degraded soils reduce plant productivity, which reduces herbivore carrying capacity, which in turn constrains predator populations. The late Permian soil record suggests that this foundational layer of terrestrial ecosystems was already weakening before the main extinction interval began. Marine ecosystems faced an analogous challenge in the form of changing carbonate chemistry. The shells and skeletal structures of many Permian marine invertebrates, brachiopods, bryozoans, echinoderms, and certain mollusks were constructed from calcium carbonate minerals whose stability in seawater depends on the concentration of carbonate ions. As carbon dioxide dissolves in seawater, it forms carbonic acid, which reduces carbonate ion concentration and makes the precipitation of calcium carbonate more energetically costly for organisms that build mineralized structures. Geochemical proxies from late Permian marine sediments indicate fluctuations in ocean carbonate chemistry during this period, suggesting that shell-building organisms were already operating in a chemically variable environment that periodically challenged their ability to maintain skeletal integrity. What emerges from the cumulative evidence is a picture of a biosphere not in crisis, but not in comfort either. The organisms of the late Permian were functional, abundant and ecologically integrated, but they were operating closer to their physiological margins than the apparent richness of their ecosystems might suggest. Oxygen was limited, temperatures were elevated, soils were under stress, ocean chemistry was variable. The buffering capacity of the biological system, its ability to absorb perturbation without fundamental reorganization, had been gradually reduced by these background stresses over the course of the late Permian. In systems theory, this condition is described as reduced resilience. The system continues to function normally under ordinary conditions, but has a diminished capacity to recover from external shocks. The Permian biosphere, by the close of the period, had accumulated enough background stress to lower its recovery threshold considerably. It did not need a perturbation of infinite magnitude to collapse. It needed a perturbation large enough to push systems that were already near their limits past the point from which recovery was possible. The geological record indicates that such a perturbation was already, at this moment in Earth history, in its earliest stages of development, rooted not in biology, not in astronomy, but in the slow and immense mechanics of the planet's own interior. The earliest signs of the end-Permian extinction were not dramatic. They did not announce themselves through sudden visible catastrophe or immediate large-scale collapse. Instead, they appeared first in the most sensitive components of the marine ecosystem, the small, the sessile, the physiologically constrained as quiet, incremental reductions in population density and species presence that would have been imperceptible to any observer without the perspective of deep time. The fossil record, examined at high stratigraphic resolution across multiple geographic sections, reveals a pattern of ecological deterioration that began well before the main extinction horizon, accumulating slowly through the late Permian in a sequence of losses that only in retrospect can be recognized as the opening phase of the largest biological crisis in Earth's history. Among the first groups to register measurable decline were the smaller, more specialized marine invertebrates organisms with narrow environmental tolerances, limited mobility, and physiological systems closely calibrated to the stable ocean conditions that had prevailed across much of the Permian. Foraminifera, single-celled protists that secreted calcium carbonate shells and lived in vast numbers across Permian seafloors and in the water column, show evidence of diversity reduction beginning several 100,000 years before the main extinction pulse. These organisms are among the most sensitive biological indicators of ocean chemistry and temperature change, and their fossil record is sufficiently continuous across many Permian sections to permit detailed quantitative analysis. What that analysis reveals is a pattern of selective extinction, certain morphological groups disappearing while others persist, consistent with a marine environment undergoing gradual chemical and thermal stress rather than a single, instantaneous shock. Radiolaria, silica-secreting protists that inhabited the open ocean water column, show a similar pattern of pre-extinction diversity reduction. Because radiolarians lived in the photic and subphotic zones of the open ocean rather than in shallow shelf environments, their decline provides evidence that conditions were deteriorating not only in nearshore settings but across the broader oceanic system. The siliceous oozes that radiolarian remains contributed to deep-sea sediments become thinner and less diverse in late Permian sections, a subtle but measurable signal embedded in the rock record that documents the contraction of viable habitat in open ocean environments. Bryozoans, the colonial filter feeders that had been ecologically significant components of Permian reef and seafloor communities for hundreds of millions of years, began showing reduced colony sizes and narrowing geographic distributions during the late Permian. Bryozoan reefs, which had formed complex three-dimensional structures providing habitat for dozens of associated species, were among the most biologically productive environments in Permian seas. Their gradual deterioration visible in the stratigraphic record as a thinning and simplification of reef-associated sedimentary faces had consequences that extended far beyond the bryozoans themselves. As reef framework complexity declined, the organisms dependent on that framework for shelter, feeding substrate, and reproductive habitat were correspondingly affected. Species that had existed in stable association with bryozoan reef communities for millions of years found their habitat contracting in ways that had no precedent within their evolutionary history. Brachiopods, despite their overall abundance in Permian seas, show evidence of compositional change during the late Permian that precedes the main extinction event. Certain brachiopod genera, particularly those with thicker, more heavily mineralized shells, and those restricted to specific depth zones or water chemistry conditions, began declining in abundance and geographic range, while more generalist forms temporarily maintain their populations. This differential pattern is ecologically informative. It indicates that the environmental changes underway were not random in their biological impact. They were selective, affecting physiologically sensitive or ecologically specialized forms first, while leaving more tolerant generalists temporarily intact. This selectivity is a characteristic signature of environmental stress operating at subcatastrophic intensity sufficient to eliminate organisms at the margins of viability, but not yet sufficient to overwhelm the entire system. The reef ecosystems of the Tethys Sea were among the most structurally complex marine environments of the Permian, built over millions of years through the accumulated growth and skeletal deposition of corals, bryozoans, sponges, and associated calcifying organisms. By the late Permian, these reef systems were already in measurable decline. Rugose and tabulate corals, the primary framework builders of Permian reefs, show reductions in colony density and species diversity in the uppermost Permian sections of reef-associated carbonate sequences. The gaps left by declining coral populations were not consistently filled by other framework builders, resulting in a net reduction in reef structural complexity and a corresponding loss of the ecological services those structures provided. In shallow shelf environments, where light penetration and nutrient availability had historically supported high biological productivity, sedimentary records from the late Permian show increasing evidence of episodic anoxia intervals during which dissolved oxygen in bottom waters fell to levels lethal to most aerobic organisms. These anoxic events, recorded in the sediment as thin, finely laminated organic-rich layers interbedded with normal bioturbated sediment, indicate that the oxygen minimum zone in shallow shelf seas was expanding and shoaling, moving upward in the water column and encroaching on habitats that had previously been reliably oxygenated. Organisms living on or near the seafloor in these environments experienced repeated unpredictable episodes of oxygen depletion, each of which imposed mortality on populations that had no evolutionary mechanism for anticipating or escaping such conditions. The fish of Permian seas, while more mobile than sessile invertebrates and therefore capable of avoiding localized deteriorating conditions, were nonetheless affected by the broader ecological changes underway. Fish populations depend on the invertebrate communities that form the lower tiers of marine food webs, filter feeders, deposit feeders, and small mobile invertebrates that in turn depend on microbial productivity, dissolved nutrient availability, and stable oxygen conditions. As those lower tiers began to thin and simplify, the food resources available to fish populations were correspondingly reduced. The effects at higher trophic levels were not immediate, but they were cumulative, and the fossil record from late Permian marine vertebrate assemblages shows a gradual reduction in the diversity and abundance of fish fauna in the sections immediately preceding the main extinction horizon. On land, the earliest signs of ecological stress were less clearly preserved, partly because terrestrial depositional environments are less continuous and less chemically informative than marine sedimentary sequences. However, palynological records, the fossil record of spores and pollen grains preserved in fine-grained sediments from several late Permian continental sections, show evidence of vegetation change that predates the main extinction. Interval. Shifts in the relative abundance of different spore and pollen types indicate changes in plant community composition, with some analyses suggesting a reduction in forest cover and an increase in stress-tolerant, opportunistic plant forms in certain regions during the late Permian. Soil faunas, which are rarely preserved directly but can be inferred from trace fossil assemblages and the organic content of paleosol profiles, appear to have declined in diversity and abundance in some late Permian continental sections. The organisms responsible for decomposition and nutrient cycling in terrestrial soils, nematodes, mites, collembolans, and microbial communities, leave only indirect evidence in the rock record, but the changes visible in paleosol chemistry and structure during the late Permian are consistent with reduced biological activity in soil systems. This reduction in soil biological activity would have had measurable consequences for plant productivity and therefore for the herbivore populations dependent on vegetation as their primary energy source. What the pre-extinction fossil record documents across both marine and terrestrial environments is a biological system losing complexity from its most vulnerable edges inward. Specialists disappear before generalists. Sensitive physiological groups decline before tolerant ones. Structurally complex ecosystems simplify before they collapse entirely. The pace of these changes, measured in hundreds of thousands of years rather than the thousands of years that would characterize the main extinction pulse, meant that no individual organism or population experienced them as crisis. Generations lived and died within conditions that, locally and temporarily, remained within survivable ranges. The deterioration was real, measurable, and directional, but it was embedded in timescales that biological systems could not perceive. The geological record preserves this pre-extinction interval with increasing clarity as analytical techniques improve. Isotopic measurements, biostratigraphic correlation, and sedimentological analysis across dozens of globally distributed sections have collectively established that the end Permian extinction was not a single instantaneous event, but the culmination of a deterioration that had been accumulating quietly and without biological awareness across the final hundreds of thousands of years of the Permian period. The organisms disappearing in this early phase left no successors in their ecological roles. The gaps they left in food webs and ecosystem structures were real, and they weakened the overall resilience of the biological system at precisely the moment when the largest and most rapid phase of environmental disruption was about to begin. Beneath the landmass that would become northern Siberia, a column of superheated mantle material had been ascending toward the base of the lithosphere for an interval measured in millions of years. The precise timing and duration of this thermal anomaly's development remain subjects of active research, but the geological consequences of its arrival at the surface are preserved with extraordinary clarity in the rock record. Beginning approximately 252 million years ago and continuing across an interval estimated at between 1 and 2 million years in total duration, a volcanic province of unprecedented scale began to form across what is now the Siberian Craton. The structures produced by this event, collectively known as the Siberian Traps, represent one of the largest accumulations of flood basalt on Earth's surface, covering an area estimated at 5 million square kilometers and containing a total lava volume that current estimates place at between 1 and 4 million cubic kilometers. These figures require context to be meaningfully interpreted. Modern volcanic eruptions, even large ones, release material measured in cubic kilometers or tens of cubic kilometers over days to weeks. The eruptions that built the Siberian traps released volumes orders of magnitude larger, not in single events, but in repeated, sustained pulses that each dwarfed anything in the modern volcanic record. Individual lava flows within the Siberian trap sequence reach thicknesses of tens to hundreds of meters, extending laterally across distances of hundreds of kilometers physical dimensions that indicate eruption rates and durations far outside the range of any volcanic event observed in human history or recorded in the geological record of the past several million years. The immediate physical consequences of eruptions at this scale were local and regional in their first expression. Lava flows advancing across the Siberian landscape at rates determined by their temperature, viscosity, and the topography they encountered would have incinerated vegetation across areas of thousands of square kilometers per individual flow event. The heat released at the flow margins, temperatures at the lava surface exceeding 1000 degrees Celsius would have been lethal to any animal within direct proximity. Terrestrial animals in the immediate eruption zones had limited options. Those capable of sustained locomotion could move away from advancing flows, provided the flows were slow enough relative to animal movement speeds to permit escape. Those with limited mobility, many invertebrates, burrowing species, nesting animals, would have been killed directly by heat, burial under ash, fall, or suffocation as local atmospheric oxygen was consumed by the combustion of vegetation. The animals of the Siberian region at the onset of the trap's volcanism inhabited ecosystems that had no evolutionary context for volcanic activity at this scale. Permian terrestrial faunas had existed through a long interval of relative geological quiescence across the Siberian Craton. The behavioral responses available to them were those shaped by the selective pressures of their actual evolutionary history responses to predators, to seasonal climate variation, to resource scarcity. Nothing in that history had prepared populations for the specific combination of stimuli produced by large-scale volcanism: intense radiant heat from multiple directions simultaneously, persistent toxic gas emissions at ground level, darkened skies from ash loading, and the destruction of vegetation across areas larger than any individual animal's home range or migratory circuit. Movement away from eruption centers would have been the primary behavioral response of mobile terrestrial animals. Large therapsids, capable of covering tens of kilometers per day under sustained locomotion, could in principle move considerable distances from active lava fields within days to weeks. The direction of that movement would have been determined by terrain, by the location of water sources, and by the distribution of remaining vegetation, all of which were being simultaneously altered by the eruptions themselves. Animals moving away from volcanic activity in one direction might encounter ash-covered landscapes, acidified water sources, or the territories of other displaced populations in another. The ecological space into which displaced animals moved was not empty or unoccupied. It was already filled with established populations whose own resources were under stress. Ashfall from the Siberian traps eruptions would have extended far beyond the immediate lava fields. Volcanic ash, carried by atmospheric circulation patterns, can travel thousands of kilometers from source vents before settling. Fine ash particles suspended in the upper atmosphere reduce incoming solar radiation and lower surface temperatures on timescales of months to years following major eruption events. Coarser ash fall Accumulating on vegetation at sufficient depth physically damages and kills plants by blocking photosynthesis, collapsing leaf structures, and altering soil chemistry through the introduction of volcanic minerals. The geographic extent of meaningful ash impact from eruptions of Siberian Traps magnitude would have encompassed regions far removed from the eruption centers themselves, potentially including large areas of northern Pangaea, where animal populations had no direct exposure to lava flows, but were nonetheless affected by the secondary consequences of volcanism operating at continental scale. The gas emissions associated with the Siberian Traps eruptions were, in terms of their long-range environmental impact, more consequential than the lava flows themselves. Flood basalt volcanism releases several categories of climatically and chemically significant gases. Sulfur dioxide, emitted in quantities estimated at tens of thousands of teragrams over the full duration of the Traps eruptive sequence, combines with atmospheric water vapor to form sulfuric acid aerosols that scatter incoming solar radiation and produce acid precipitation across vast areas downwind of eruption centers. Carbon dioxide, released both directly from magma degassing and indirectly through the contact metamorphism of carbon-rich sedimentary rocks beneath the advancing lava, including coal deposits, evaporites, and carbonate sequences present in the Siberian Craton's geology, contributed to a progressive increase in atmospheric greenhouse gas concentrations. The contact metamorphism component of Siberian Traps gas release is considered by current research to have been particularly significant. As magma intruded into and beneath carbon-rich sedimentary sequences, it baked those sediments at temperatures sufficient to drive off large quantities of carbon dioxide, methane, and thermogenic gases without necessarily producing surface lava flows. Estimates of the carbon released through this mechanism vary considerably between studies, but the consensus position in current literature is that contact metamorphism substantially amplified the total carbon output of the Siberian Trap system beyond what direct volcanic degassing alone would have produced. This amplification is important because it helps account for the magnitude of the geochemical signals preserved in the end Permian rock record, carbon isotope excursions, ocean acidification indicators, and temperature proxy records, which are larger than volcanic degassing models based solely on lava volume would predict. For terrestrial animals at distances of hundreds to thousands of kilometers from the eruption centers, the first perceptible environmental signals of the Siberian Traps activity would not have been lava or ash, but atmospheric and climatic changes operating on seasonal to decadal timescales. Sulfur dioxide injection into the stratosphere produces cooling effects that persist for 1 to several years per major eruptive pulse before the aerosols settle and are removed. If eruptive pulses recurred on timescales shorter than the atmospheric residence time of sulfate aerosols, the cooling effect would have been sustained rather than episodic. Animals adapted to specific temperature ranges would have experienced growing season shortening, altered precipitation patterns, and unpredictable seasonal timing disruptions to the environmental cues that govern reproduction, migration, and food availability. The behavioral ecology of Permian vertebrates under these conditions can be partially reconstructed from what is known about their physiology and the environments they inhabited. Reptiles and the more basal therapsid lineages, whose thermoregulation was at least partially dependent on environmental heat sources, would have been immediately affected by temperature reductions associated with volcanic aerosol loading. Reduced ambient temperatures would have lowered activity levels, extended periods of torpor, or reduced metabolism, and decreased reproductive success in temperature-sensitive species. For populations already operating near the margins of their thermal tolerance ranges, as many interior Pangaea species were during periods of seasonal cold, even modest cooling could push mortality rates above reproductive. Replacement rates, initiating population decline without any direct exposure to volcanic hazards. Herbivore populations dependent on plant communities that were themselves responding to changed light availability, altered precipitation, and volcanic ash deposition faced food supply disruptions that compounded the direct physiological effects of atmospheric change. A large herbivore requiring hundreds of kilograms of vegetation per week to maintain body mass in a landscape where plant productivity had declined by even 20 to 30% would have experienced the deficit as a chronic energy. Shortfall not immediately lethal, but cumulatively debilitating across a season or a year. Population-level effects of sustained nutritional stress include reduced reproductive rates, increased juvenile mortality, and increased vulnerability to disease and parasitism, all of which reduce population growth rates and accelerate decline under conditions of continued environmental deterioration. The fossil record from the earliest phase of the end Permian extinction interval preserves evidence consistent with this pattern of progressive, geographically expanding ecological disruption. Vertebrate fauna, assemblages from sections spanning the onset of the trap's volcanism, show the beginnings of compositional change. Not yet the catastrophic losses of the main extinction horizon, but measurable reductions in the diversity and abundance of large-bodied herbivores and their associated predator guilds. The world that had supported dense populations of dicynodonts, gorgonopsians, and temnospondyls across broad regions of Pangaea was beginning, slowly and without any single dramatic threshold event, to contract around its inhabitants. The vegetation of Pangaea had taken hundreds of millions of years to establish its distribution across the supercontinent's varied landscapes. Plant communities had colonized every environment capable of supporting photosynthesis, from humid coastal lowlands, where dense forests of seed ferns and chordata grew in continuous canopy, to semi-arid interior margins where drought-tolerant forms persisted through seasonal water deficits, to the high southern latitudes where glossopterid forests tracked the limits of polar light availability. What the volcanic forcing of the Siberian traps introduced was not variability of a familiar kind. It was directional, sustained, and operating simultaneously across multiple environmental parameters that plant communities had never experienced changing in concert at this rate and magnitude. The combustion of vegetation by advancing lava flows was the most direct mechanism of plant destruction, but it was geographically restricted to regions within reach of individual flow fronts. Far more consequential in terms of total biomass impact was the combination of acid precipitation, ash deposition, elevated temperatures, and altered atmospheric composition affecting plant communities across continental and eventually global scales. Sulfur dioxide emissions from the Siberian traps, upon contact with atmospheric moisture, formed sulfuric acid that returned to the surface in precipitation, with pH values potentially reaching 2 to 3 inches, heavily affected regions. At these acidity levels, leaf cuticles, the waxy protective layers regulating water exchange, were progressively degraded. Stomatal function was disrupted, reducing photosynthetic efficiency and increasing water loss across affected vegetation zones. Soil chemistry responded to acid precipitation on timescales of years to decades. The buffering capacity of soils, their ability to neutralize incoming acidity through chemical reactions with mineral components, is finite. As repeated acid precipitation events exhausted soil buffering reserves, pH values at the root zone declined, mobilizing aluminum and other metal ions toxic to plant root systems at elevated concentrations. Aluminum toxicity inhibits cell division, disrupts nutrient uptake, and ultimately kills root tissue, compromising the plant's ability to access water and minerals regardless of whether surface conditions temporarily improved. The damage therefore penetrated the functional foundations of plant growth, undermining resource acquisition systems on which all above-ground biomass production depended. The palynological record fossil spores and pollen, preserved in fine-grained sediments, provides the most detailed available evidence of vegetation response across the end-Permian interval. In section after section, from sites distributed across multiple paleocontinents, the same fundamental pattern emerges. Diverse assemblages of gymnosperm pollen, reflecting the mixed forests of the late Permian, give way to assemblages dominated by fern spores. This transition reflects the collapse of seed plant-dominated communities and a temporary reversion to pioneer vegetation in which ferns, with their faster reproductive cycles and greater tolerance for disturbed substrates, occupied the ecological space vacated by dying forests. Fern. Spike events' sharp increases in fern spore abundance relative to gymnosperm pollen are preserved in latest Permian and earliest Triassic sections from Greenland, Antarctica, Australia, and China. Their geographic consistency is significant. It indicates that vegetation collapse was not a regional phenomenon, but a global pattern, reflecting the replacement of complex forest communities by simplified pioneer vegetation across the entire land surface of Pangaea. The forests of the Permian, the ecological infrastructure that had supported every terrestrial food web for hundreds of millions of years, were being reduced, within geologically brief intervals, to ghost landscapes of fern-covered ground and standing dead wood. For the herbivore populations dependent on those forests, the consequences were direct. A large dicynodont, consuming several hundred kilograms of vegetation per week, required a landscape capable of continuously regenerating that biomass within its foraging range. When plant productivity collapsed, when living vegetation density fell below the threshold required to meet maintenance energy requirements, the herbivore faced conditions with no sustainable resolution. Movement toward remaining productive zones offered temporary relief, but the vegetation collapse was geographically expanding faster than large animals could permanently relocate. The movement of herbivore populations in response to habitat deterioration produced ecological concentrations in remaining productive areas, followed by rapid overexploitation of those areas' vegetation, followed by further collapse of food availability in the refugia themselves. Animals congregating in shrinking productive zones exhausted local plant communities faster than those communities could regenerate, converting temporary refugia into additional zones of scarcity. This process accelerated the overall rate of herbivore population decline far beyond what the simple reduction in total vegetation productivity alone would have caused. Predator populations tracked these dynamics with a temporal lag, determined by individual body reserves. A large Gorgonopsian could survive extended periods without successful prey capture by drawing on stored body fat and reducing activity levels. But survival across longer intervals required prey population densities sufficient to sustain successful hunting. As herbivore populations declined, hunting success rates fell proportionally. The energy cost of each unsuccessful pursuit multiplied across an increasing number of failed attempts per successful kill, progressively depleted individual body condition. Animals in declining body condition reproduce less successfully, are more vulnerable to injury, and have reduced immune function, compounding population-level decline initiated by prey scarcity. Soil ecosystems, which process dead organic matter and cycle nutrients back into forms accessible to living plants, were among the most severely disrupted components of the terrestrial system. The death of large forest areas produced an initial pulse of organic material that soil decomposer communities would normally process over years to decades. But the chemical environment required for that decomposition had been fundamentally altered. Acidified soils, reduced microbial diversity, and disrupted fungal networks compromised the decomposition pathway, leaving dead organic matter to accumulate rather than cycle. Coals and carbonaceous shales from the Permian-Triassic boundary interval preserved in sections from Australia, China, and elsewhere record this decomposition failure directly. Accumulations of plant material that normal soil biological activity failed to process, indicating collapse of the fungal and microbial communities responsible for terrestrial nutrient cycling. This disruption created a feedback that further constrained plant community recovery. Even in areas where direct stresses had temporarily eased, degraded soil systems lacked the biological infrastructure to support rapid vegetation regrowth. Nutrients remained locked in undecomposed organic matter rather than being mineralized and made available to growing plants. The mycorrhizal fungal networks facilitating nutrient and water uptake in seed plant root systems had been severely damaged, leaving surviving plant propagules without the symbiotic partnerships on which their establishment depended. The landscape had lost not simply its vegetation, it had lost the biological machinery required to efficiently rebuild it. The chain reaction initiated by vegetation collapse extended through every tier of the terrestrial ecosystem simultaneously. Herbivores lost food, predators lost prey. Soil communities lost the stable chemical environment required for decomposition. Plant communities lost the soil biological support required for regeneration. Each of these losses reinforced the others in interlocking feedbacks that drove the terrestrial system progressively further from any recoverable state. The forests of Pangaea had been the foundation on which hundreds of millions of years of terrestrial evolution had constructed its most complex expression. Their collapse was not simply an event in the history of plants, it was the removal of the structural basis on which the entire terrestrial biosphere rested. The atmosphere that Permian animals had evolved within was already, by the standards of later geological periods, a physiologically demanding medium. Oxygen concentrations near 16% had imposed measurable constraints on aerobic metabolism and sustained activity levels across most vertebrate lineages. That atmosphere, challenging as it was, had been stable enough across sufficient time for animals to adapt their physiology and behavior to its specific properties. What the Siberian Traps volcanism introduced was not a stable new baseline. It was a directional, accelerating chemical transformation of the atmosphere, operating faster than evolutionary response times, allowed a shift in fundamental atmospheric composition that progressively narrowed the physiological space within which complex animal life could function. Carbon dioxide concentrations rose substantially across the end Permian interval. Geochemical proxies preserved in paleosol carbonates, marine sediments, and boron isotope records collectively indicate that atmospheric carbon dioxide may have increased by a factor of 4 to 8 times pre-extinction baseline values during peak volcanic forcing. Current estimates place pre-extinction concentrations at approximately 500 to 900 parts per million, with values potentially reaching 3,000 to 8,000 parts per million during the most intense interval. The uncertainty ranges in these figures are substantial, reflecting the difficulty of reconstructing precise atmospheric composition from 252 million year-old proxy records. The directional signal, however, a large and rapid increase, is consistent across multiple independent proxy systems. Elevated carbon dioxide affects vertebrate physiology through hypercapnia, the accumulation of carbon dioxide in the bloodstream, which acidifies blood pH and impairs the oxygen-carrying function of hemoglobin. The Bohr effect describes the relevant mechanism precisely. As blood pH falls, hemoglobin's affinity for oxygen decreases, reducing oxygen delivery to tissues even when oxygen is being inhaled. For the synapsids of the late Permian, this meant that rising carbon dioxide was not simply an additional stressor operating alongside low oxygen. It was a stressor that directly amplified the physiological impact of low oxygen by degrading the efficiency of the very system responsible for compensating for it. Animals already operating near their aerobic limits, under 16% atmospheric oxygen, faced a simultaneous deterioration in the efficiency with which that oxygen could be used. Temperature increases driven by greenhouse gas accumulation added a further dimension to the respiratory crisis. Metabolic oxygen demand in ectothermic animals scales directly with ambient temperature as surface temperatures rose. The oxygen requirements of reptiles and more basal therapsid lineages increased proportionally, while atmospheric oxygen availability remained fixed or declined. This compression of aerobic scope, rising demand, meeting falling supply, left increasingly narrow physiological margins between the oxygen required for basic maintenance metabolism and the oxygen available from the surrounding air. For many species, that margin was eventually eliminated entirely. The body size record of vertebrates across the Permian-Triassic boundary preserves measurable evidence of these physiological pressures. A phenomenon documented across multiple surviving lineages, known as the Lilliput effect, involves a consistent reduction in average body size within groups that persisted through the extinction interval. Fossil assemblages from earliest Triassic sections show smaller-bodied representatives of surviving lineages compared to their late Permian predecessors. Smaller bodies have higher surface area to volume ratios, improving heat dissipation under elevated temperatures, and have lower absolute oxygen requirements, reducing the physiological cost of maintaining aerobic metabolism under oxygen-limited conditions. The body size reduction visible in early Triassic vertebrate faunas is a measurable biological response to the specific atmospheric stresses of the end Permian crisis, not a taxonomic artifact. Methane released from volcanic degassing and from the destabilization of seafloor methane hydrates as ocean temperatures rose contributed additional greenhouse forcing. Methane is approximately 80 times more potent than carbon dioxide as a greenhouse gas over a 20-year horizon. Its atmospheric oxidation to carbon dioxide and water over years to decades also consumed atmospheric oxygen directly, providing a chemical pathway through which methane release contributed to oxygen depletion in addition to its warming effect. The combined carbon dioxide and methane forcing drove surface temperature increases that current proxy records, including oxygen isotope ratios in marine carbonates and the distribution of heat-sensitive sedimentary faces. Estimate at between 8 and 15 degrees Celsius above pre-extinction baselines in tropical and subtropical regions. Hydrogen sulfide, produced in anoxic ocean waters by sulfate-reducing bacteria, may have reached atmospheric concentrations sufficient to cause direct toxicity in terrestrial animals during the most severe phases of the crisis. Under normal ocean circulation, hydrogen sulfide generated in deep anoxic waters is oxidized before reaching the surface. As end Permian ocean circulation slowed and deep water anoxia expanded, this oxidative buffer was progressively overwhelmed. The presence of isoreniaratane, a biomarker produced exclusively by anaerobic photosynthetic bacteria requiring both hydrogen sulfide and light in Permian-Triassic boundary sediments from multiple locations, indicates that hydrogen sulfide-producing bacteria reached the photic zone, confirming that hydrogen sulfide evasion to the atmosphere was occurring. Hydrogen sulfide is toxic to aerobic organisms at concentrations of parts per million, inhibiting cytochrome C oxidase, the enzyme responsible for the final step of mitochondrial respiration, and producing rapid incapacitation at sufficient concentrations. For terrestrial animals, episodic atmospheric hydrogen sulfide contamination represented a threat with no behavioral solution. Unlike food, scarcity, or heat, toxic atmospheric chemistry was invisible, pervasive, and produced no directional signal that animal sensory systems could detect and respond to before physiological damage had already begun. The neurological and respiratory effects of hydrogen sulfide poisoning at lethal concentrations operate on timescales of minutes, leaving no interval during which behavioral avoidance could be effective. The ultraviolet radiation environment also changed significantly during the end Permian crisis. Halogen-rich gases released by the Siberian traps, including chlorine and bromine compounds derived from evaporite deposits intruded by magma, contributed to stratospheric ozone depletion. Current models suggest ozone column reductions of 50 to 70% over mid-latitudes were possible during peak volcanic forcing. Increased ultraviolet B radiation at the surface damages DNA in proportion to exposure duration and intensity. The fossil record preserves direct evidence of elevated mutation rates during the end Permian in the form of malformed spores and pollen teratological grains found in boundary sections from multiple geographic locations, indicating that the ultraviolet environment was sufficiently altered to produce measurable genetic damage across living plant populations. The combined atmospheric deterioration of the end Permian, therefore, operated through multiple simultaneous chemical and radiative pathways. Rising carbon dioxide impaired acid-base regulation in vertebrate blood. Declining effective oxygen availability reduced aerobic scope. Rising temperatures increased metabolic demand while reducing oxygen solubility in body fluids. Episodic hydrogen sulfide produced direct cytotoxic effects at the cellular level. Elevated ultraviolet radiation imposed mutagenic stress on dividing cells across all surface-exposed organisms. No single stressor alone was necessarily sufficient to drive global mass extinction at the scale the fossil record documents. Operating in combination, reinforcing each other through interlocking physiological mechanisms, they created an atmospheric environment that progressively exceeded the tolerance limits of the vast majority of complex animal life that had spent hundreds of millions of years evolving under the conditions of a world that no longer existed. While the terrestrial biosphere was contracting under the combined pressures of vegetation collapse, atmospheric deterioration, and rising temperatures, the marine realm was undergoing its own transformation, one that followed a distinct but parallel trajectory rooted in the same volcanic forcing. The oceans of the late Permian had supported diverse, structurally complex ecosystems for hundreds of millions of years. Their biological communities built on layered food webs anchored by filter feeders, reef builders, and microbial primary producers had demonstrated resilience across multiple prior perturbation events. What the end Permian crisis delivered to marine systems was not a perturbation within the range of prior experience. It was a simultaneous shift in temperature, chemistry, and circulation operating at a rate and magnitude that exceeded the adaptive and migratory capacity of the vast majority of marine organisms. Ocean warming was the most pervasive initial stressor. As atmospheric carbon dioxide and methane concentrations rose, the ocean surface absorbed heat through direct atmospheric contact, raising sea surface temperatures across all latitudes. Proxy records from oxygen isotope ratios in marine carbonates and from the distribution of temperature-sensitive sedimentary minerals indicate that tropical sea surface temperatures during the peak end Permian crisis interval reached values between 35 and 40 degrees Celsius. In some regions, temperatures at or beyond the upper thermal tolerance limits of most marine invertebrates alive at the time. Modern coral reefs begin experiencing bleaching and mortality at sustained temperatures of 30 to 32 degrees Celsius, and the calcifying organisms of Permian seas had similarly constrained thermal windows within which normal physiological function was possible. The relationship between temperature and oxygen solubility in seawater is a physical constraint with no biological workaround. As water temperature rises, the maximum concentration of dissolved oxygen that seawater can hold decreases. At 35 degrees Celsius, seawater holds approximately 40% less dissolved oxygen than at 20 degrees Celsius under equivalent atmospheric conditions. For marine animals dependent on extracting dissolved oxygen across gill surfaces or through diffusion across body walls, this reduction in oxygen availability imposed the same compounding respiratory stress that terrestrial animals experienced through atmospheric changes, but delivered through the medium of warming water rather than altered air. Composition. Marine organisms in tropical and subtropical shelf environments, where warming was most acute, faced dissolved oxygen concentrations declining toward hypoxic thresholds even in surface waters that had previously been well oxygenated. Ocean circulation slowed substantially as the temperature gradient between equatorial and polar waters decreased. Under normal conditions, this gradient drives thermohaline circulation, the density-driven overturning of ocean water that transports oxygen-rich surface water to depth and brings nutrient-rich deep water to the surface. As polar regions warmed and the equator to pole temperature difference contracted, the driving force for this circulation weakened. Reduced overturning meant that deep ocean waters received less oxygen replenishment from the surface. Organic matter settling from the productive surface ocean continued to consume oxygen through decomposition in the deep water column, but the rate of oxygen resupply through circulation declined faster than the rate of oxygen consumption. The result was the progressive expansion of oxygen minimum zones depth intervals in which dissolved oxygen concentrations fell to levels lethal to most aerobic organisms both laterally across the ocean floor and vertically, upward into shallower water. The brachiopods, which had been among the most abundant and diverse components of Permian seafloor communities for hundreds of millions of years, were acutely vulnerable to the combination of warming and deoxygenation. Most brachiopod genera occupied fixed positions on the seafloor, attached to substrate by a muscular stalk or cemented directly to hard surfaces. Their inability to relocate in response to deteriorating local conditions made them entirely dependent on the continued suitability of their immediate environment. As bottom water oxygen concentrations declined in shelf and deeper environments, and as temperatures rose beyond their thermal tolerance ranges, brachiopod populations experienced mortality that could not be offset by migration. Fossil abundance data from uppermost Permian marine sections show a dramatic reduction in brachiopod density and diversity beginning at the extinction horizon, with many genera that had maintained stable populations for tens of millions of years disappearing within intervals too brief to resolve stratigraphically at most localities. Rugose and tabulate corals, the primary framework builders of Permian reef systems, were similarly constrained by their sessile habit and their narrow thermal and chemical tolerances. Coral calcification, the process by which coral polyps extract calcium and carbonate ions from seawater to build their skeletons, is sensitive to both temperature and the carbonate saturation state of surrounding water. As temperatures rose and ocean acidification progressed, both the energetic cost of calcification and the physical stability of existing carbonate structures increased and decreased, respectively requiring more energy to build new skeleton while simultaneously accelerating the dissolution of existing framework. The combination produced a reef-building crisis in which coral population growth rates fell below the rates of framework erosion and dissolution, causing reef structures to shrink and simplify rather than grow and diversify. Crinoids stalked echinoderms that had formed dense filter-feeding aggregations on Permian seafloors declined sharply across the extinction interval. Their dependence on stable, well-oxygenated bottom water and their low tolerance for temperature extremes made them highly vulnerable to the specific combination of stresses operating during the end Permian crisis. Crinoid-rich carbonate faces, common in middle Permian sections, become dramatically reduced in abundance in the uppermost Permian, replaced in some sections by microbial mats and stromatolitic structures, indicators of conditions too extreme for most metazoan life, but tolerable for certain prokaryotic communities. The appearance of microbial mats and stromatolites in end Permian and earliest Triassic marine sections is one of the most ecologically significant signals in the boundary rock record. Stromatolites, layered structures built by mat-forming cyanobacteria and other microorganisms, had been the dominant form of marine life for the first 3 billion years of Earth history. Before the evolution of animals capable of grazing on and burrowing through microbial mats suppressed their formation, their reappearance in latest Permian and earliest Triassic shallow marine environments indicates a collapse of the metazoan ecological controls that had kept microbial mat formation in check across the preceding hundreds of millions of Ramsar years. When the animals that grazed on, burrowed through, and physically disrupted microbial communities died, the microbes expanded into the ecological space vacated by complex life. Ammonoids, free-swimming cephalopods that had occupied predatory and scavenging roles in Permian open water and shelf environments, experienced severe population reduction during the extinction interval, though certain lineages survived as a remnant that would later diversify into the highly successful Triassic ammonoid fauna. Their partial survival, relative to the near-total elimination of sessile filter feeders, reflects the advantage of mobility in a crisis defined by rapidly shifting environmental gradients. An ammonoid capable of swimming vertically and horizontally in search of oxygenated water had options unavailable to a brachiopod cemented to a seafloor that was becoming anoxic. Mobility did not guarantee survival. The crisis was too pervasive and too sustained for most mobile lineages to escape its full consequences, but it provided a marginal buffer that appears, in the fossil record, as slightly higher survival rates among actively swimming forms compared to sessile or low-mobility taxa. Fish populations, occupying higher trophic positions in marine food webs, experienced the collapse of the invertebrate communities that formed the base of their food supply. Even fish species capable of tolerating the direct physical and chemical stresses of the end Permian Ocean faced an ecological crisis as prey availability declined toward levels insufficient to sustain viable populations. The marine vertebrate record from the Permian-Triassic boundary is less complete than the invertebrate record, but available data indicate substantial reductions in fish diversity and abundance across the extinction interval, with the earliest Triassic marine vertebrate fauna being both taxonomically depauperate and ecologically simplified relative to the diverse assemblages of the late Permian. What the oceans were undergoing across this interval of tens of thousands of years was a systematic dismantling of the ecological architecture that had been assembled across the entire Paleozoic era. The reef systems, the filter feeder communities, the layered trophic structures of shelf and open ocean environments, All were being reduced by the simultaneous operation of warming, deoxygenation, acidification, and the secondary ecological consequences of losing the organisms that maintained ecosystem function. The sea that had supported the greatest marine biodiversity in Earth's history to that point was being transformed, progressively and without reversal on any timescale relevant to the organisms living through it, into something fundamentally and profoundly different. The deoxygenation of Permian ocean waters did not proceed uniformly across all depths and regions simultaneously. It advanced as an expanding frontier beginning in the deep ocean basins where circulation was already sluggish, then spreading upward and outward into intermediate and shallow water environments that had previously been reliably oxygenated. This spatial progression produced a staggered pattern of ecological collapse that the stratigraphic record preserves across globally distributed marine sections, each recording the arrival of lethal conditions at different times depending on local depth, geography, and circulation connectivity. In the deep ocean, anoxic conditions had been intermittently present throughout much of the Permian, confined to basins with restricted circulation. As end Permian warming reduced the density contrast between surface and deep waters, ventilation of these basins declined further. The sedimentary record from deep water environments shows a transition from bioturbated sediments indicating the presence of burrowing organisms to finely laminated, organic-rich deposits recording the complete absence of metazoan seafloor life. This transition, visible in drill cores and outcrop sections from multiple ocean basin margins, marks the biological death of deep seafloor communities across broad areas. As the oxygen minimum zone expanded vertically, its upper boundary rose through the water column, compressing marine communities toward the surface and toward higher latitudes where cooler water retained marginally higher oxygen concentrations. The chemistry of end Permian seawater was simultaneously being altered by volcanic sulfur input. Sulfur dioxide released by the Siberian traps contributed to ocean surface acidification and to sulfate accumulation in the water column. Under the anoxic conditions prevailing in deep and intermediate waters, sulfate-reducing bacteria metabolize this sulfate, producing hydrogen sulfide as a metabolic byproduct. Hydrogen sulfide is directly toxic to aerobic organisms. It inhibits cytochrome C oxidase, the terminal enzyme of the mitochondrial electron transport chain, at concentrations measured in parts per million. Its accumulation in water masses that were episodically mixed into shallower environments represented a direct chemical kill mechanism operating independently of and in addition to the physical stresses of warming and oxygen depletion. The biogeochemical evidence for widespread hydrogen sulfide accumulation is preserved in the molecular fossil record. Isoraniaeratane, an organic compound produced exclusively by green sulfur bacteria requiring simultaneous access to light and hydrogen sulfide, has been identified in Permian Triassic boundary sediments from southern China, Italy, and the western United States. Because these bacteria can only inhabit the photic zone, the uppermost 200 meters of the water column, their presence in boundary sediments indicates that hydrogen sulfide had risen from deep anoxic waters into the sunlit upper ocean. This condition, known as photic zone euxenia, represents one of the most lethal configurations of ocean chemistry possible for complex aerobic life, as it places toxic hydrogen sulfide in direct contact with the organisms and primary producers concentrated in surface waters. Photic zone euxenia would have been catastrophic for phytoplankton, the photosynthetic microorganisms forming the base of the marine food web. Their direct poisoning by hydrogen sulfide removed the foundational energy input to the entire marine ecosystem. Carbon isotope records from end Permian marine sections show a pronounced negative excursion, a sharp decrease in the ratio of carbon 1:3 to carbon 12 inches marine carbonates, consistent with a large and rapid reduction in marine biological productivity. The magnitude of this isotopic shift, estimated at 3 to 5 per mil across many sections, requires the removal of a substantial fraction of the ocean's photosynthetically active biomass within a geologically brief interval. The collapse of primary productivity propagated through the trophic structure of marine ecosystems simultaneously. At multiple levels, zooplankton declined as phytoplankton fell, and larger predators faced collapsing prey availability while simultaneously enduring the direct physical stresses of warming and oxygen depletion. The trilobites arthropods that had inhabited marine environments for over 270 million years, surviving multiple prior extinction events, did not survive the end Permian crisis. Their disappearance from the fossil record at the Permian-Triassic boundary ends one of the longest-running lineages in animal evolutionary history. Their sensitivity to carbonate saturation state, which affected their calcified exoskeletons, and their dependence on the seafloor communities being eliminated by anoxia and eusynia, provide plausible pathways to their extinction. The fusulinid foraminifera large, reef-associated protists with elaborate calcified shells, ecologically significant for approximately 80 million years, disappeared entirely at the same boundary. Their extinction, alongside the rugose and tabulate corals, removed from the marine ecosystem entire groups of organisms that had played structural roles in carbonate platform construction across an enormous span of geological time. Dead zones expanded across the continental shelves that had previously been the most productive regions of the Permian Ocean. Organisms dying in these zones settled to the seafloor and accumulated as organic-rich sediment rather than being processed through normal decomposition pathways. This represented a massive withdrawal of biological material from active nutrient-cycling carbon, nitrogen, and phosphorus locked into anoxic sediment rather than being regenerated and made available to surviving primary producers. The nutrient impoverishment of surface waters resulting from this sequestration further suppressed phytoplankton recovery, sustaining low productivity conditions even during intervals when direct volcanic forcing may have temporarily moderated. The feedback was self-reinforcing. Dead zones suppressed productivity reduced the biological activity that might otherwise have helped restore oxygen to deeper waters, and reduced oxygen allowed dead zones to persist and expand. The reefs that had characterized Permian's shallow marine environments for hundreds of millions of years underwent physical dissolution as ocean acidification progressed. Carbonate undersaturation conditions, in which seawater is chemically aggressive toward calcium carbonate minerals, spread across shelf environments, attacking the skeletal material of living and dead reef-building organisms simultaneously. Reef frameworks that had taken millions of years to construct were chemically degraded within thousands of years, removing the three-dimensional habitat complexity that had supported the most diverse marine communities of the Paleozoic. The seafloors left behind were not simply empty, they were chemically hostile to the re-establishment of calcifying communities, extending the duration of biological absence well beyond the interval of peak environmental stress. What replaced the complex Permian marine ecosystem across this interval was a system of dramatically reduced ecological complexity. Microbial mats, communities of bacteria and archaea forming laminated structures on seafloors, expanded into the ecological space vacated by metazoan communities. Their proliferation, recorded in the distinctive microbialite and stromatolite faces of earliest Triassic marine sections, represents a reversion to a biological configuration not widespread in marine environments since the Precambrian. The reappearance of these structures is not simply a curiosity of the stratigraphic record. It is a direct measure of how completely the ecological controls that complex animal life had exerted over marine environments, grazing, burrowing, predation, competition had been removed by the extinction event. The marine mass die-off of the end Permian was the convergent outcome of multiple simultaneous chemical and physical insults: warming, deoxygenation, acidification, euxinia, productivity collapse, and nutrient sequestration operating across all ocean depths and geographic regions within a time frame too brief for evolutionary adaptation and too severe for ecological reorganization to compensate. What had been the most diverse marine ecosystem in Earth's history was reduced, within tens of thousands of years, to a system dominated by microbial communities and the chemical signatures of biological collapse preserved in sediment accumulating on a largely lifeless seafloor. The terrestrial environments of Pangaea had been losing biological complexity for an extended interval before the most acute phase of the end Permian crisis arrived. Vegetation had simplified. Herbivore populations had declined. Soil systems had lost biological function. But the land surface had retained, through the earlier phases of environmental deterioration, enough structural continuity to support surviving animal populations in diminished but functional ecosystems. What the peak phase of the end Permian crisis delivered to terrestrial environments was a further and more severe set of stresses that eliminated that residual habitability across most of the land surface, transforming large regions of Pangaea from impoverished but survivable landscapes into environments that could not sustain complex animal life at all. Surface temperatures across tropical and subtropical Pangaea reached values during the peak crisis interval that current proxy records derived primarily from oxygen isotope ratios in phosphatic fossils and from the distribution of temperature-sensitive clay minerals in paleosol sequences estimate at between 50 and 60 degrees Celsius in low-latitude continental interiors. These are not simply uncomfortable temperatures, they exceed the upper thermal tolerance limits of virtually all known complex terrestrial animals. Protein denaturation in most vertebrate tissues begins at sustained temperatures above approximately 45 degrees Celsius. Enzymatic function, membrane integrity, and the molecular machinery of cellular respiration are all compromised at temperatures that approach and exceed this threshold. For large-bodied animals with limited capacity for behavioral thermoregulation unable to seek deep shade, cool water, or underground refuge sufficient to buffer against extreme ambient heat, sustained surface temperatures in this range were lethal regardless of the state of the atmosphere, the food supply, or any other environmental variable. The geographic distribution of this lethal heat was not uniform across Pangaea. Thermal gradients existed between equatorial regions and higher latitudes, and between continental interiors and coastal zones where oceanic influence provided some degree of temperature moderation. Evidence from the distribution of tetrapod fossils across the Permian-Triassic boundary suggests that animal populations were increasingly restricted to higher latitude refugia and to coastal environments where temperatures remained below the lethal threshold for sustained periods. The equatorial belt of Pangaea, a region that had previously supported some of the highest terrestrial biodiversity on the supercontinent, appears, on the basis of the near-complete absence of tetrapod fossils from low-latitude continental sections spanning the boundary interval, to have become effectively uninhabitable for large terrestrial vertebrates during the peak crisis. This latitudinal compression of habitable terrestrial space had consequences that extended beyond the direct thermal mortality of animals in equatorial regions. As populations retreated toward higher latitudes, the total land area available to support viable animal communities contracted. Populations that had previously been distributed across broad geographic ranges were concentrated into smaller areas with reduced resource availability. The ecological dynamics of population compression, overexploitation of local food resources, increased competition between species, elevated predation pressure on reduced prey populations, and the demographic consequences of small population size, including reduced genetic diversity and increased vulnerability to stochastic extinction, all operated simultaneously within these refugia, accelerating the rate of species loss beyond what direct environmental mortality alone would have produced. Acid rain, generated by the reaction of volcanic sulfur dioxide and nitrogen oxides with atmospheric moisture, affected terrestrial environments across the full geographic range of the volcanic gas plume. pH values in precipitation reaching the land surface in heavily affected regions would have been sufficient to damage plant tissues directly, to acidify freshwater systems to levels lethal for most aquatic organisms, and to accelerate the chemical weathering of exposed rock surfaces in ways that further degraded soil structure and fertility. Freshwater ecosystems, rivers, lakes, and wetlands that had supported temnospondyl amphibians, early reptiles, and diverse invertebrate communities throughout the Permian were acutely vulnerable to acidification. Their inhabitants had no mechanism for buffering against rapid pH changes in the water they inhabited and breathed through, and the fossil record from freshwater depositional environments spanning the Permian-Triassic boundary shows sharp reductions in the diversity of aquatic vertebrates and invertebrates consistent with widespread freshwater. Acidification events. The destruction of terrestrial vegetation had, by the peak crisis interval, proceeded to the point where large areas of the land surface were effectively bare. Without plant root systems binding soil particles and regulating water infiltration, the physical integrity of soils deteriorated rapidly. Erosion rates increased substantially, documented in the sedimentary record by a characteristic change in the texture and composition of fluvial deposits spanning the Permian-Triassic boundary, a transition from the laterally stable, channel-confined river deposits characteristic of vegetated landscapes to the broad, sheet-like flood deposits of braided river systems, which develop when vegetation loss eliminates the bank stabilization and flow regulation that rooted plants provide. This sedimentary signature, preserved in boundary sections from South Africa, Antarctica, Russia, and Australia, indicates that the hydrological behavior of Pangea river systems changed fundamentally as vegetation cover was lost, a change that would have further degraded the freshwater environments on which many surviving animal populations depended. Ultraviolet radiation reaching the land surface during intervals of peak ozone depletion imposed additional stress on surviving organisms. Terrestrial animals exposed to elevated ultraviolet B radiation experience DNA damage in skin and eye tissues at rates proportional to exposure duration and radiation intensity. For animals active during daylight hours, which included most of the large-bodied vertebrates of the Permian, there was no behavioral option that fully eliminated ultraviolet exposure without also eliminating the ability to forage, reproduce, and carry out the other activities essential to survival. Nocturnal behavior could reduce but not eliminate exposure. Burrowing could provide protection during peak radiation hours but required suitable substrate and imposed its own energetic and ecological constraints. The mutagenic and carcinogenic effects of sustained elevated ultraviolet exposure would have reduced reproductive success and increased developmental abnormalities in exposed populations, contributing to demographic decline even in individuals that survived the acute physiological stresses of the crisis environment. The interaction between heat stress and the degraded atmospheric oxygen environment created a physiological trap with no escape for many terrestrial vertebrate lineages. At high ambient temperatures, the metabolic rate of ectothermic animals increases, raising their oxygen demand. Simultaneously, the respiratory efficiency of gas exchange across lung surfaces decreases as blood temperature rises and the oxygen-carrying capacity of hemoglobin is reduced. Animals caught between elevated metabolic oxygen demand and reduced respiratory efficiency in an atmosphere already depleted of oxygen were physiologically constrained in ways that no behavioral adjustment could fully compensate. The only organisms capable of maintaining function under these combined stresses were those small enough to exploit microclimatic refugia burrows, rock crevices, the understory of surviving vegetation patches where temperatures and radiation levels were locally reduced below the lethal thresholds prevailing at open surface conditions. Toxic metal mobilization from acidified soils and weathering rock surfaces contributed an additional chemical stressor to terrestrial environments. Aluminum, manganese, and heavy metals released by acid-driven weathering accumulated in soil water and were transported into rivers and lakes. These metals are toxic to plant root systems, to freshwater invertebrates, and to the vertebrates that consumed contaminated water and food. Their accumulation in food chains, with concentrations increasing at each trophic level through biomagnification, meant that predators at the top of surviving food webs were exposed to the highest metal concentrations, adding physiological stress to lineages already under pressure from every other dimension of the crisis environment. What the land surface of Pangaea had become at the peak of the end Permian crisis was an environment hostile to complex life across the majority of its area. Heat excluded large animals from equatorial regions. Acid rain degraded freshwater systems and soils across broad mid-latitude zones. Ultraviolet radiation imposed mutagenic stress on all surface-active organisms. Atmospheric chemistry reduced the physiological effectiveness of respiration. Toxic metals contaminated water and food chains. Vegetation was absent or severely reduced across vast areas, removing the food resources and physical habitat structure on which terrestrial food webs depended. The stressors did not operate independently or sequentially. They were simultaneous, geographically overlapping, and mutually reinforcing in their biological effects. The terrestrial biosphere that had taken hundreds of millions of years to build had been reduced, within a geologically negligible interval, to a collection of marginal refugia in which a small fraction of surviving lineages persisted under conditions representing the absolute limits of biological tolerance. The end Permian mass extinction represents the most severe reduction in biological diversity in the history of complex animal life on Earth. The scale of loss, reconstructed from the fossil record across thousands of stratigraphic sections on every continent and in marine sequences from every major ocean basin, is without precedent in the 540 million year history of the Phanerozoic eon. Current estimates, derived from comprehensive taxonomic databases and corrected for the variable preservation potential of different organism groups and depositional environments, indicate that approximately 96% of all marine species and approximately 70% of all terrestrial vertebrate species disappeared within the extinction interval. These figures, already extraordinary in their magnitude, likely underestimate the true extent of biological loss because the fossil record preserves only a fraction of the organisms that existed: soft-bodied species, small-bodied forms, and organisms from environments with low preservation potential are systematically underrepresented in the record from which extinction estimates are calculated. The temporal structure of the extinction, as revealed by high-resolution stratigraphic analysis of boundary sections, was not perfectly instantaneous even by geological standards. Evidence from the most precisely dated and most continuously deposited sections, including the Meishan section in southern China, which has become the global reference section for the Permian-Triassic boundary, indicates that the main pulse of extinction was geologically abrupt, occurring within an interval estimated at between 60,000 and 105,000 years. This is an extraordinarily brief duration for an extinction of this magnitude. For context, the end Cretaceous mass extinction that eliminated the non-avian dinosaurs approximately 66 million years ago, itself considered geologically rapid, occurred within a comparable or slightly longer interval, eliminated a far smaller proportion of existing species. The end Permian extinction was both faster and more complete than any other mass extinction in the Phanerozoic record. Within the marine realm, the losses were taxonomically comprehensive in a way that no prior extinction event had approached. The elimination of 96% of species translated into the disappearance of entire higher taxonomic groups, not just individual species or genera, but entire orders and families that had been stable components of marine ecosystems for hundreds of millions of years. The rugose corals, which had built reef systems since the Ordovician period, approximately 450 million years ago, were completely eliminated. The tabulate corals, another ancient reef-building group with similarly deep evolutionary roots, disappeared entirely. The trilobites, whose origins extended back to the Cambrian explosion over 500 million years ago, vanished from the fossil record at the Permian-Triassic boundary, ending a lineage that had persisted through 4 prior mass extinction events. The fusulinid foraminifera, the blastoid echinoderms, and multiple families of brachiopods that had dominated seafloor communities across the entire Paleozoic era were eliminated without leaving any descendant lineages. The concept of background extinction, the steady, low-level disappearance of species that occurs continuously through geological time as a result of competition, environmental change, and evolutionary replacement, provides a useful baseline against which the end Permian losses can be measured. Under background extinction conditions, the average species persists for approximately 1 to 10 million years before disappearing, and new species arise at rates approximately equal to extinction rates, maintaining overall diversity levels. The end Permian extinction represented a deviation from background rates by several orders of magnitude. Extinction rates during the main pulse were estimated at hundreds to thousands of times the background level, compressing into tens of thousands of years a volume of biological loss that would under normal conditions have required tens to hundreds of millions of years to accumulate. The selectivity of the extinction, the pattern of which organisms survived and which did not, provides important information about the mechanisms responsible for the losses. Several selectivity patterns are consistently observed across the end Permian fossil record. Organisms with high metabolic rates and precise physiological requirements for stable temperature, oxygen, and pH conditions were disproportionately eliminated. Organisms with low metabolic rates, broad environmental tolerances, and small body sizes were disproportionately represented among survivors. Sessile organisms with limited ability to relocate in response to deteriorating local conditions suffered higher extinction rates than mobile organisms capable of tracking shifting environmental gradients. These patterns are consistent with the specific stresses that operated during the end Permian crisis: warming, deoxygenation, acidification, and atmospheric deterioration, and provide independent corroboration of the environmental reconstruction derived from geochemical and sedimentological evidence. In marine environments, the differential survival of organisms with low metabolic rates is particularly well documented. Among brachiopods, the groups that survived into the Triassic were disproportionately those with simpler shell mineralogy, smaller body sizes, and inferred lower metabolic demands. Among echinoderms, certain holothurian lineages, sea cucumbers, with their relatively simple body plans and low metabolic requirements, survived while the more metabolically demanding crinoids and echinoids experienced severe losses. Among fish, the groups that persisted through the boundary were generally those capable of tolerating broad ranges of temperature and oxygen concentration. The pattern repeated consistently across phyla and across geographic regions. Physiological flexibility and low metabolic demand were the primary determinants of survival probability in the end Permian marine extinction. On land, the vertebrate losses were severe, but showed a different selectivity pattern, reflecting the different stresses operating in terrestrial environments. Large-bodied animals, which require proportionally greater food resources and have longer generation times, reducing the rate at which populations can recover from mortality events, were disproportionately eliminated. The Gorgonopsians, the dominant apex predators of late Permian terrestrial ecosystems, disappeared entirely at or near the extinction horizon. Their elimination removed from terrestrial food webs the entire guild of large active predators that had structured vertebrate community dynamics across the Permian. The dinocephalians had already disappeared in an earlier extinction pulse. Several families of dicynodonts, the dominant herbivores of Permian landscapes, were eliminated, though certain dicynodont lineages survived into the earliest Triassic. The losses among terrestrial invertebrates, though less completely documented than the vertebrate record, appear to have been equally or more severe. Insect diversity, reconstructed from the fossil record of insect body fossils and from trace fossil evidence of insect activity in plant material, shows a marked reduction across the Permian-Triassic boundary. Several insect orders that had been present through the Permian disappeared entirely or were reduced to remnant lineages. The loss of insect diversity had cascading consequences for plant reproduction. Many Permian plant groups depended on insects for pollination and for the decomposer communities that processed dead organic matter in terrestrial ecosystems. The functional impacts of insect extinction therefore extended well beyond the insects themselves, propagating through ecosystem processes in ways that compounded the direct losses of plant and vertebrate diversity. The fungi record from the Permian-Triassic boundary deserves particular attention as an indicator of the scale of terrestrial biological collapse. In several boundary sections from continental depositional environments, a distinctive spike in fungal spore abundance is preserved immediately above the last diverse plant and animal assemblages of the Permian. This fungal spike, representing a massive proliferation of saprotrophic fungi feeding on dead organic matter, is interpreted as a direct response to the enormous pulse of dead biomass produced by the simultaneous death of plant and animal communities across vast areas. The presence of this spike in sections from multiple continents indicates that the terrestrial die-off was geographically synchronous and biologically comprehensive. The fungi were responding to a global pulse of mortality that left sufficient dead organic material to support their proliferation across the land surface of Pangaea. What the end Permian extinction removed from the biosphere was not simply a large number of species. It removed entire ecological functions, evolutionary lineages representing hundreds of millions of years of diversification, and the biological infrastructure through which energy and nutrients had flowed through Permian ecosystems. The reef-building function in marine environments was eliminated for approximately 5 million years following the extinction, the longest reef gap in the Phanerozoic record. The apex predator function in terrestrial vertebrate communities was eliminated and required millions of years of evolutionary diversification among surviving lineages before it was fully reconstituted. The filter feeding function in shallow marine environments, previously dominated by brachiopods and bryozoans, was dramatically reduced and restructured as bivalve mollusks, a group that survived the extinction, with relatively lower losses, gradually expanded into the ecological roles vacated by the eliminated groups. The 96% figure, precise as it sounds, is ultimately an abstraction that inadequately conveys what was lost. Behind each percentage point lies an entire species, a unique evolutionary lineage, a distinct ecological role, a set of physiological and behavioral adaptations refined across millions of years of natural selection. The end Permian extinction eliminated not just individuals and populations, but the irreplaceable products of evolutionary time operating across scales that dwarf anything in human experience. What remained after the main extinction pulse was not a damaged version of the Permian world. It was a fundamentally different biological system, impoverished, simplified, and populated by the small fraction of survivors whose particular combination of physiological tolerance, ecological flexibility, and circumstantial location had allowed them to persist through conditions that eliminated nearly everything else alive on Earth. In the immediate aftermath of the end Permian extinction, the land surface of Pangaea was occupied by a biological community bearing almost no resemblance to the diverse, ecologically structured world that had preceded it. The complex food webs, the layered trophic relationships, the specialized ecological roles filled by dozens of vertebrate families all had been stripped away, leaving a simplified and spatially fragmented assemblage of survivors whose presence in the earliest Triassic fossil record reflects not ecological success in any conventional sense, but the marginal persistence of lineages that had, through some combination of physiological tolerance and circumstantial positioning, remained on the survivable side of the extinction threshold. The most ecologically dominant terrestrial vertebrate of the earliest Triassic was Lystrosaurus, a dicynodont therapsid whose fossil remains are found in early Triassic continental sections from Antarctica, South Africa, India, Russia, and China, making it one of the most geographically widespread large vertebrates known from any period in Earth's history. Lystrosaurus was not a large or imposing animal by the standards of its Permian predecessors. Most species fell within a body mass range of roughly 10 to 100 kilograms, considerably smaller than many of the dicynodont genera that had dominated Permian herbivore guilds. Its skull morphology, characterized by a downturned beak, reduced dentition, and robust jaw structure, indicates adaptation to processing tough, low-quality vegetation, a dietary strategy well suited to a world in which plant communities had been severely reduced in diversity and productivity. The physiological characteristics of Lystrosaurus that likely contributed to its survival are interpretable from its skeletal anatomy and from comparisons with related therapsid lineages. Its barrel-shaped thorax suggests a large lung volume relative to body size, a morphological feature that would have increased respiratory efficiency under the low oxygen, high carbon dioxide atmospheric conditions of the latest Permian and earliest Triassic. Its compact, robust limb bones indicate a heavily built body plan associated with low-intensity, energy-conservative locomotion rather than the sustained high-speed activity of predatory lineages. Its inferred metabolic flexibility, the capacity to reduce metabolic rate during periods of resource scarcity, is consistent with the survival of a lineage through an extinction interval defined in large part by food web, collapse, and resource limitation. The dominance of Lystrosaurus in earliest Triassic continental faunas was so complete that paleontologists have described the earliest Triassic terrestrial ecosystem as a Lystrosaurus monoculture, a characterization that, while simplified, captures a genuine and extraordinary feature of the post-extinction biological landscape. In some early Triassic fossil assemblages, Lystrosaurus skeletal material constitutes over 90% of the identifiable vertebrate remains. This numerical dominance of a single genus across a geographically vast area has no parallel in the Permian record, where vertebrate faunas were characterized by high taxonomic diversity and relatively even distribution of abundance across multiple genera and families. The collapse of that diversity into near monoculture dominance by a single survivor lineage is itself a measure of how completely the ecological structure of the Permian terrestrial world had been dismantled. Other terrestrial vertebrate survivors of the end Permian extinction were present in earliest Triassic faunas alongside Lystrosaurus, though in far lower abundance and diversity than the pre-extinction assemblages from which they descended. Certain cynodont therapsids, the lineage from which mammals would eventually arise, survived the extinction, represented in early Triassic sections by small-bodied genera occupying predatory or omnivorous ecological roles. Their small body sizes inferred high metabolic flexibility and probable capacity for burrowing behavior, which would have provided thermal refuge during the peak heat stress of the crisis interval, are consistent with survival through the specific combination of stresses that characterized the end Permian environment. The cynodonts that persisted into the Triassic were not the dominant animals of their ecosystems, but their survival preserved the evolutionary lineage from which the entire mammalian radiation would eventually emerge hundreds of millions of years later. Early archosaurs, members of the reptilian lineage that would eventually give rise to crocodilians, pterosaurs, and dinosaurs, were present in earliest Triassic continental faunas as small to medium-bodied predators. Their survival reflects the broader pattern of reptilian resilience through the extinction interval, attributable in part to the lower metabolic rates and greater physiological tolerance for environmental variability that characterize ectothermic lineages relative to the more metabolically demanding therapsid predators that were eliminated. The Gorgonopsians, the apex predators of the Permian, had disappeared entirely, leaving the large predator niche vacant in earliest Triassic ecosystems. The archosaurs that survived were not yet capable of filling that niche at comparable body sizes, and the earliest Triassic therefore lacked functional large predators in the terrestrial realm for a substantial interval following the extinction. In the marine realm, the survivors of the end Permian extinction were similarly characterized by physiological breadth rather than ecological sophistication. Certain bivalve mollusks, clams, and their relatives survived with comparatively lower losses than most other marine invertebrate groups. Their tolerance for low oxygen conditions, their capacity to reduce metabolic activity during environmental stress, and their ability to exploit a wide range of food sources, including deposited organic matter, made them effective survivors in the degraded ocean environments of the earliest Triassic. In the ecological vacuum left by the elimination of brachiopods, bryozoans, and reef-building corals, bivalves expanded in abundance and began occupying filter-feeding roles in shallow marine environments that brachiopods had dominated across the entire Paleozoic. Certain gastropod lineages survived the extinction and persisted into earliest Triassic marine environments, as did some ammonoid cephalopods whose partial survival from what appears to have been a very small number of founding lineages would eventually seed the diverse ammonoid faunas of the Mesozoic. The survival of ammonoids from such a severe bottleneck is itself informative about the mechanisms of their persistence. Their mobile, free-swimming habit, their ability to regulate buoyancy and move vertically through the water column in search of oxygenated water, and their relatively rapid reproductive cycles, which shorten the generation time available for population recovery, all contributed to their persistence through conditions that eliminated sessile and slow reproducing marine invertebrates with far greater efficiency. Among marine vertebrates, certain fish lineages survived the extinction, though with substantially reduced diversity relative to their Permian predecessors. The earliest Triassic marine fish fauna was taxonomically impoverished and ecologically simplified, dominated by generalist forms capable of tolerating the warm, oxygen-depleted, chemically variable waters of the post-extinction ocean. The complex predator-prey relationships and trophic specializations of Permian marine vertebrate communities were absent, replaced by a simplified system in which surviving fish occupied broad ecological roles in an environment with few competitors and drastically reduced prey diversity. The microbial realm bacteria, archaea, and simple eukaryotic microorganisms had survived the extinction essentially intact in terms of metabolic diversity, though specific community compositions shifted in response to changed environmental conditions. Microbial communities are far more resistant to the types of environmental perturbation that drive animal and plant extinctions because their short generation times, measured in hours to days rather than years to decades, allow evolutionary adaptation to occur on timescales relevant to the environmental changes themselves. The proliferation of microbial mats in earliest Triassic marine environments and the fungal blooms documented in terrestrial boundary sections represent the expansion of microbial and fungal communities into the ecological space vacated by the eliminated complex life. In this sense, the earliest Triassic world was not biologically empty, it was microbiologically active, but the complex, multicellular, ecologically structured life that defines what most observers mean by a living world had been reduced to isolated remnants persisting in marginal conditions. The survivors of the end Permian extinction shared, across their considerable biological diversity, a common characteristic that transcends the specific physiological or ecological features of any individual lineage. They were organisms that had, either through ancestral adaptation or through the specific circumstances of their geographic location at the time of peak crisis intensity, maintained reproductive populations through conditions that eliminated 96% of their contemporaries. They were not, in most cases, the dominant, specialized, ecologically sophisticated organisms of the Permian world. They were its generalists, its small-bodied forms, its physiological tolerance, the organisms that the complex Permian ecosystem had accommodated without featuring, and whose moment of ecological relevance arrived only when everything built above them had been removed. The earliest Triassic was not simply a world recovering from catastrophe. It was a world in which the conditions that had produced the catastrophe persisted in modified but still biologically hostile form across an interval far longer than the extinction event itself. The geological and geochemical evidence from earliest Triassic sections indicates that the environmental stresses of the end Permian crisis, elevated temperatures, depressed atmospheric oxygen, ocean anoxia, and reduced biological productivity did not resolve rapidly following the main extinction pulse. They lingered, fluctuated, and in some cases intensified during the early Triassic, creating a prolonged interval of environmental instability that suppressed biological recovery for millions of years after the extinction horizon. Temperature proxy records from earliest Triassic, marine, and terrestrial sections indicate that surface temperatures remained substantially elevated above pre-extinction baselines for an extended interval following the main extinction. Pulse. Oxygen isotope data from conodont apatite, a high-resolution temperature proxy derived from the phosphatic skeletal elements of early Triassic marine organisms, indicate that tropical sea surface temperatures remained between 32 and 38 degrees Celsius through much of the early Triassic, with some estimates suggesting peak values exceeding 40 degrees Celsius during certain intervals. These temperatures were not simply warm, they were at or beyond the upper thermal tolerance limits of most complex marine organisms, meaning that the ocean surface in tropical regions remained physiologically hostile to the establishment of diverse, metabolically active communities for millions of years after the extinction itself had concluded. The carbon cycle, severely disrupted by the end Permian volcanic forcing and the collapse of biological productivity, did not stabilize rapidly following the extinction. Carbon isotope records from earliest Triassic marine carbonates show repeated negative excursions, sharp decreases in carbon, 1,3 relative to carbon, 1,2 superimposed on an already depleted baseline. These repeated isotopic anomalies, documented in sections from multiple ocean basins and interpreted as indicating repeated pulses of isotopically like carbon input to the ocean atmosphere system, suggest that the Siberian Traps volcanic system continued to contribute carbon to the atmosphere during the early Triassic, and that additional sources of carbon release, including the oxidation of accumulated dead organic matter on land and the continued destabilization of seafloor methane hydrates, sustained atmospheric carbon dioxide at elevated levels well beyond the main extinction interval. The biological system that would normally buffer carbon cycle perturbations through photosynthetic carbon fixation and carbonate precipitation had been so severely reduced in productive capacity that its regulatory function compromised. Ocean anoxia persisted across the early Triassic, with a geographic extent and intensity that current research suggests may have equaled or exceeded that of the extinction interval itself in certain regions. Sedimentological evidence from early Triassic marine sections, including the continued presence of laminated, organic-rich faces indicating the absence of benthic organisms, and geochemical indicators of sulfidic bottom waters, documents the persistence of anoxic and euthynic conditions across broad areas of the seafloor for millions of years following the extinction horizon. The recovery of bottom water oxygen concentrations required the restoration of thermohaline circulation, which in turn required the cooling of surface waters and the re-establishment of the temperature gradients between equatorial and polar regions that drive ocean overturning. As long as surface temperatures remained elevated, the physical mechanism for ocean ventilation remained impaired, and the seafloor anoxia that had contributed so directly to the extinction continued to prevent the re-establishment of diverse benthic communities. The reef gap, the interval following the end Permian extinction during which marine carbonate reef systems were absent from the geological record, extended for approximately 5 million years into the Triassic. This is the longest reef gap in the Phanerozoic record, reflecting the combined effects of the elimination of all Permian reef-building organisms, the persistence of ocean chemistry hostile to carbonate precipitation, and the absence of surviving lineages capable of immediately reconstituting reef framework construction. The return of reef-building activity in the Middle Triassic, when new groups of scleractinian corals, an entirely different coral lineage from the rugose and tabulate corals of the Paleozoic, began constructing carbonate frameworks, required not only the evolution of new reef-building organisms, but the prior restoration of ocean temperatures, carbonate saturation states, and oxygen levels to ranges within which calcification was physiologically and chemically feasible. Terrestrial ecosystem recovery was similarly delayed by the persistence of hostile environmental conditions and by the absence of the biological components necessary for ecosystem reconstruction. The restoration of diverse plant communities required not simply the survival of plant propagules, but the recovery of the soil biological systems, mycorrhizal networks, decomposer communities, nitrogen-fixing bacteria that support plant establishment and growth. These soil biological systems had been severely disrupted during the extinction interval, and their recovery proceeded on timescales governed by microbial generation times and ecological succession dynamics rather than by the rate of environmental improvement alone. Paleobotanical records from earliest Triassic continental sections show that diverse gymnosperm-dominated plant communities did not immediately replace the pioneer fern vegetation that had colonized the post-extinction landscape. The recovery of structurally complex multi-layered plant communities was a gradual process that extended across millions of years of the early and middle Triassic. The coal gap, an interval in the earliest Triassic, during which coal deposits are essentially absent from the geological record, despite the presence of terrestrial depositional environments, provides independent evidence of the Phrygian Atif. Failure of terrestrial ecosystem function during this period. Coal forms from the accumulation and compaction of plant material in waterlogged environments, where decomposition is inhibited by anoxic conditions. Its absence in earliest Triassic sections does not reflect the absence of waterlogged depositional environments. Fluvial and lacustrine systems continued to operate, but rather the absence of sufficient plant productivity to generate the organic matter inputs from which coal could form. The earliest Triassic landscape simply did not produce enough living plant biomass to leave a coal record, a testimony to the severity of the vegetation crisis that persisted well into the recovery interval. The vertebrate fossil record from earliest Triassic continental sections reflects the biological simplicity of post-extinction terrestrial ecosystems with considerable clarity. Faunal assemblages from this interval are characterized by low taxonomic diversity, high numerical dominance by a small number of generalist species, absence of large-bodied apex predators, and a near-complete lack of the ecological specialization that had characterized Permian vertebrate communities. The Lystrosaurus-dominated assemblages of the earliest Triassic persisted with relatively little compositional change across the first 1 to 2 million years of the period, indicating that ecological succession, the process by which pioneer communities are replaced by progressively more complex and diverse assemblages, was proceeding extremely slowly in the absence of the environmental stability and biological diversity required to support it. Repeated extinction pulses during the early Triassic further impeded recovery. The fossil record from this interval documents at least 2 additional extinction events of moderate severity occurring within the first 5 million years of the Triassic intervals, during which diversity increases that had tentatively begun were reversed by renewed environmental deterioration. The causes of these secondary extinctions remain subjects of active research, but evidence points to continued volcanic activity, repeated carbon cycle perturbations, and the persistence of ocean anoxia as contributing factors. The biological systems attempting to recover from the end Permian extinction were doing so in an environment that remained fundamentally unstable, subject to recurring perturbations that reset ecological succession and prevented the accumulation of the biological complexity necessary for stable, diverse ecosystems. The simplification of ecosystems during the earliest Triassic extended to the structure of food webs themselves. Trophic chains. The sequences of feeding relationships linking primary producers to apex predators were shorter and less complex than those of the Permian. Fewer trophic levels existed because the diversity of organisms capable of filling intermediate ecological roles had been so severely reduced. Energy flow through post-extinction ecosystems was dominated by microbial pathways, decomposition and chemosynthesis rather than by the photosynthesis-based, herbivore-mediated pathways that characterize complex terrestrial and marine ecosystems. This microbially dominated energy flow was energetically less efficient at supporting large-bodied, metabolically demanding animals, providing a further constraint on the recovery of vertebrate diversity and abundance. The earliest Triassic world was, in the most literal biological sense, a diminished planet. Not diminished in physical scale, not diminished in geological activity, not diminished in the basic chemical and physical processes that sustain planetary systems, but diminished in the complexity, diversity, and ecological integration of its living components in a way that had no precedent in the history of complex life. The organisms that persisted through this interval did so in a world that offered fewer ecological opportunities, fewer biological interactions, and fewer evolutionary pathways than any world their lineages had inhabited since the Cambrian diversification of animal life. Recovery was not impossible. The fossil record documents that it eventually occurred, but it was slow, interrupted, and contingent on the gradual restoration of environmental conditions that the living world had lost the capacity to rapidly rebuild on its own. The restoration of biological complexity following the end Permian extinction was not a single, continuous process that began immediately after the last extinction pulse and proceeded smoothly toward the diverse ecosystems of the later Mesozoic. It was an uneven, geographically variable, and repeatedly interrupted sequence of ecological and evolutionary events that unfolded across tens of millions of years, a recovery interval so prolonged that it encompassed within its later stages the origin and early diversification of the lineages that would eventually dominate Mesozoic ecosystems, including the archosaurs that gave rise to dinosaurs, pterosaurs, and the ancestors of modern birds and crocodilians. The earliest phase of biological recovery, occurring within the first 1 to 2 million years of the early Triassic, was dominated by the expansion of opportunistic generalist species into the ecological vacuums created by extinction. This phase was not recovery in the sense of increasing ecological complexity, it was the filling of the most basic biological functions by whatever organisms were present and capable of surviving the still hostile environmental conditions. On land, the dominance of Lystrosaurus and a small number of Cynodont and early archosaur genera reflected the absence of competitors and predators rather than the positive ecological success of those lineages in a stable, resource-rich environment. In the ocean, the expansion of microbial mats, certain bivalve lineages, and opportunistic gastropods across seafloors previously occupied by diverse invertebrate communities similarly reflected ecological vacancy rather than biological flourishing. The stabilization of atmospheric carbon dioxide concentrations as the Siberian Traps volcanic system progressively reduced its output across the early Triassic was a necessary precondition for the subsequent cooling of surface temperatures and the restoration of ocean circulation patterns. Current geochronological constraints on the duration of Siberian Traps volcanic activity suggest that the main eruptive phase had largely concluded within 1 to 2 million years of the extinction horizon, though lower intensity volcanic activity may have continued for considerably longer. As carbon dioxide input to the atmosphere declined, the greenhouse forcing that had sustained elevated temperatures began to weaken, and proxy records from the Middle Triassic onward show a gradual reduction in tropical sea surface temperatures toward values more compatible with the establishment of diverse, metabolically active marine communities. The recovery of marine ecosystems preceded and, in some respects, enabled the recovery of terrestrial systems because the ocean's thermal inertia and chemical buffering capacity allowed marine environments to stabilize before the more variable terrestrial realm had fully recovered its biological infrastructure. The earliest signs of genuine marine ecological recovery, as opposed to the simple numerical expansion of opportunistic survivors, appear in the fossil record approximately 4 to 5 million years after the extinction. Horizon, in sections dated to the Smithian-Spathian boundary within the early Triassic. At these levels, taxonomic diversity in certain marine invertebrate groups begins to increase measurably. Body sizes increase within surviving lineages, and the first evidence of renewed ecological tiering, the vertical partitioning of ecological roles across different positions in the water column and on the seafloor, appears in the structure of preserved assemblages. The Scleractinian corals, the group that would become the primary reef builders of all subsequent geological periods, including the present, appear in the fossil record during the Middle Triassic, approximately 240 million years ago. Their origins remain a subject of ongoing research, with current evidence suggesting they evolved from soft-bodied, sea anemone-like ancestors that had survived the end Permian extinction without leaving a calcified fossil record. The appearance of Scleractinian corals capable of constructing carbonate frameworks marked the end of the 5 million year reef gap and initiated a new chapter in marine carbonate ecology, one built on entirely different biological foundations from the rugose and tabulate coral reefs of the Paleozoic. The Mesozoic reef systems that eventually developed were not reconstructions of Permian reefs. They were new ecological structures built by new organisms, organized around new sets of biological interactions. In terrestrial environments, the recovery of plant community diversity and structural complexity proceeded through a succession of stages that the paleobotanical record documents with increasing resolution. The pioneer fern-dominated vegetation of the earliest Triassic gave way, across the early and middle Triassic, to more diverse gymnosperm-dominated communities in which multiple plant growth forms ground cover, shrubs, and trees of varying heights were present simultaneously. The restoration of vertical structural complexity in plant communities had cascading effects on the animal communities they supported because multi-layered vegetation creates a diversity of microhabitats, food resources, and shelter opportunities that simple, low-diversity plant cover cannot provide. As plant communities became more structurally complex, the diversity of herbivorous insects and vertebrates that could be supported in those communities increased correspondingly. The cynodont pteropsids, which had survived the end Permian extinction as small-bodied generalists, diversified substantially during the Triassic into a range of ecological roles including herbivory, carnivory, and omnivory across a spectrum of body sizes. Their diversification produced, among other lineages, the first true mammals, small, probably nocturnal, insectivorous animals whose fossil remains appear in the late Triassic approximately 225 million years ago. These earliest mammals were not ecologically dominant. They were minor components of Triassic ecosystems, occupying the lowest tiers of vertebrate communities in terms of body size and ecological influence. Their significance lies entirely in retrospect in the knowledge that this small, inconspicuous lineage of survivors from the worst extinction in Earth's history would, following the end Cretaceous extinction 160 million years later, diversify into the dominant large-bodied vertebrates of the Cenozoic era. The archosaurs, which had been present as minor components of earliest Triassic faunas, underwent a major evolutionary radiation during the Middle and Late Triassic that fundamentally restructured terrestrial vertebrate communities. The Archosaur lineage split into two major branches: the Crurotarsi, which gave rise to crocodilians and their extinct relatives, and the Ornithodyra, which gave rise to pterosaurs and dinosaurs. By the late Triassic, archosaurs had expanded to fill a wide range of body sizes and ecological roles across terrestrial and semi-aquatic environments, including the large-bodied apex predator roles that had been vacant since the elimination of the Gorgonopsians at the end of the Permian. The diversification of archosaurs into these roles represented the completion of a process of ecological reconstruction that had begun with the survival of small, physiologically tolerant reptilian lineages through the extinction interval and had proceeded through tens of millions of years of evolutionary diversification. The dinosaurs, which first appear in the fossil record approximately 230 to 235 million years ago, in the late Triassic, were therefore not products of a world freshly recovering from the end Permian extinction. They were products of a world that had already been recovering for approximately 20 million years, in which ecological complexity had been substantially rebuilt and in which the evolutionary innovations of the Archosaur radiation had already produced a range of ecologically significant lineages. The appearance of dinosaurs within this context was not a sudden origination event, but the emergence of a particularly successful subgroup within an already diverse and ecologically structured archosaur fauna. Their subsequent rise to dominance, which accelerated following the end Triassic extinction approximately 201 million years ago, an event that eliminated many of their archosaur competitors, was the culmination of an evolutionary trajectory that had its origins in the survival of small, generalist reptilian lineages through the worst biological crisis in the history of complex life. The oceans of the Middle and Late Triassic were inhabited by increasingly diverse assemblages of marine reptiles, ichthyosaurs, nothosaurs, and eventually plesiosaurs that had evolved from terrestrial or semi-aquatic ancestors and returned to the marine environment during the Triassic recovery interval. Their appearance in marine ecosystems represented the filling of large-bodied predator roles that had been absent from the ocean since the elimination of the large marine predators of the Permian. The evolution of these lineages from terrestrial ancestors reflects a broader pattern of ecological opportunity exploitation that characterized the Triassic recovery, the vacant ecological roles left by the end Permian. Extinction were filled not by the recovery of eliminated lineages, which was impossible, but by the evolutionary diversification of surviving lineages into new body plans, new physiologies, and new ecological strategies. The biological world that existed by the end of the Triassic period, approximately 201 million years ago, was recognizably complex and ecologically structured in ways that the earliest Triassic world had not been. Marine ecosystems had rebuilt trophic complexity across multiple levels. Terrestrial ecosystems supported diverse plant communities, diverse invertebrate faunas, and vertebrate communities spanning a range of body sizes and ecological roles from small insectivorous mammals to large archosaurian predators. The recovery had been real, measurable, and biologically profound. But it had taken approximately 50 million years from the end Permian extinction at 252 million years ago to the end of the Triassic at 201 million years ago to produce a world of comparable ecological complexity to the one that had been lost. 50 million years of evolutionary time, ecological succession, and biological diversification to rebuild what the Siberian Traps volcanism and its cascading consequences had dismantled in tens of thousands of years. The asymmetry between the timescale of destruction and the timescale of recovery is perhaps the most consequential single fact that the end Permian extinction record contains a reminder, preserved in stone across every continent on Earth, of how much more rapidly complex biological systems can be reduced than they can be rebuilt.